terminal box, which is what we see right there, all set up and stuff like that. And that damper's going to be metering in the air force, and then you're going to have all your drops. So in a real room, you're going to have 4, 5, 6, right, diffusers, all flexed up, being branched off of. Okay. We won't be getting into balancing this section of the circuit because Mike Ziegler is going to take you through that. So you'll be getting into that part of testing balance. This is just kind of like the big picture. So when we talk about measuring the flow with the flow hood, we're going to be going to each one of these diffusers in a room. Okay. So that's kind of like the big picture of what we're going to be getting into. Also, I failed to mention this. Any questions, please ask. If I don't have an answer, I will give you an answer before you leave, I promise. Or one of you will something. So we'll definitely get you an answer. Don't be shy as far as answering questions. From your week's discussion, I'm sure you talked a little bit about this. There are two fundamental types of VAV boxes. Dependent and independent. We're talking about how the damper, it's important to focus on, how the damper is going to be modulated, what strategy we're going to use. That's what we talk about, dependent or independent. From your discussion, did you learn anything about one being better than the other? Any recommendations that you had in class for a VAV box being dependent or independent? Which one's better? If so, why? I'll be shy. Okay. The way it works is the dependent box is not, the independent box is the weapon of choice, if you will. This is the one that you want to use. We're going to talk about why in just a moment. The dependent box has been around a long, long time. They're not as efficient. They're not as accurate. They're not as quick to respond. So that's why the Corps would always recommend independent box. Okay. Now, they both can do single duct. Like, this is a single duct. One inlet, not two, one inlet. They both can do that. Okay. They both can satisfy dual ducts. You can have a multi-zone or some kind of hot deck, cold deck coming in, and you actually have two inlets. We don't have that here. You don't see many of those anymore, mainly because the air handlers like that aren't used as much anymore. But you have a hot deck, maybe 90 degrees, a cold deck, maybe 55 degrees. And what you're doing is you're blending the air at the box. At the box. You're not getting a constant 55 degrees in like this is. You're getting two different use, like you're taking a shower, right? You're mixing the water. Same kind of thing. They both can do baseboard. They both can do reheats, perimeter reheats, things like that. So what's the big difference? This is going to be talking about the strategy of how the box is controlling the air. What kind of strategy? So to that end, let's take a look at pressure dependent real quick. First one. This is the one that's not recommended. They're out there. It's up to the contractor what they want to use. For the VAV dependent box, what we're going to say is the damper itself, right over here, right? We're talking about this damper. That's your volume damper. That's your air. The strategy for that is going to be based upon strictly room temperature. So you have a stat on the wall, right? You see them all the time. That's an input to the VAV box. Controller. Now, that being said, I hate to do this so early in the morning, but I got to throw a graph up. So, what we're saying here is the dependent box is going to have that damper move only on a change of room temperature. Well, that makes sense. What's wrong with that? We're going to find out in just a minute. So we're going to say, okay, so we've got room temperature here. As seen by that stat, this is 75 degrees set point. whatever is called for, right? The damper, while you're occupied, it's important, it's going to travel from some minimum position to some maximum position. While you're occupied, you can never close off this. Why? Why can't you just close it off if you don't want the 55-degree air? Sorry? Yeah, ventilation. You got to have it. Actually, standards tell you that you've got to have fresh air coming in. So you're going to always operate while you're occupied from minimum up to some maximum. Maximum being full open, right? So now, as the temperature goes up, the box is going to begin to open up. Whoa, what's wrong with that? Well, let's talk about a couple of things. One of them is, how fast do you think that room stat changes? And this is where people don't think about it. Like, you have the classroom you're in. How long do you think it changes? It takes to change 1 degree Fahrenheit. 30 seconds? 5 seconds? 2 minutes? 5 minutes? That's more like it, right? So it's going to take a lot longer to get that 55-degree air coming from the main air handler, right? It's going to take that much time. So you're going to get a lag is really what I mean. It's going to be slower to respond. It's not a problem with the static. That's not the issue. It's just how long it takes the room temperature to change. How quick does it move? Okay? So you've got this, basically this built-in lag. So the question comes in now, well, why is it called dependent? I sold you this box. I said, hey, if you give me 1 inch of static pressure right here, I guarantee when that damper's full open, I guarantee 1,000 CFM. If you don't give me 1 inch of static, I'm taking all bets off the table. I have no idea what's going to go out of this box. You see the issue. So that means you've got to have 1 inch of static right here. Therefore, a dependent box is dependent on the main air handler to provide 1 inch. What if something happens and you need more cooling, and all of a sudden the air handler goes down to 3/4 of an inch? You no longer have that 1 inch of static. I have no idea what's going to come out of this box. And this thing has no idea how much CFM is going through it. So the dependent box is dependent on the main air handler to provide that much static. You get the idea. So you have these two things that go against it. And that's why they're not recommended. Any questions so far? Okay, let's take a look at the next style. All right, so how do we get around this problem? The first thing that's going to be different about an independent box is the flow pickups. Okay. On the inlet to a pressure independent box, you will have a flow pickup. This is nothing more than a pitot tube repackaged. That's all it is. Pitot tube repackaged. Now, obviously, you're not going to look in. But if you see these two hoses coming out, you know it's an independent box. That being said, is that a dependent or independent box up there? Because you can see it. Give me a neighbor, trying to test it. Is that an independent or a dependent up there? You look right up there. Independent? Sure. Why? Because I got these two hoses. That's what I got. Okay, where is this all going? Well, let me make a little drawing here. So a side view of those flow pickups. Total pressure is the impact pressure. That's the pressure right there. That's total pressure. Now we know what from your discussions in HVAC. Okay. Oh, sorry. Total pressure is static pressure plus velocity. Static pressure is what? Pressure that pushes out at all angles, right? That's what's going on. So what happens is we have two pressures, one here, a high side, and we have a low side. And that's a differential pressure. So that being the case, total pressure minus static pressure is velocity pressure. So what we're going to get out of this is velocity pressure. That's what we're going to get out of it. Okay, where's this all going here? All right. Here's what's going to happen. Now we know the differential pressure. Inside that little controller, there's software. They're going to be playing around with the software a little bit later. It's taking this velocity pressure and coming up with a calculated CFM. Oh, now this controller knows how much air is going through it. It knows what's going on. Remember, the dependent box had no idea how much CFM was traveling through that box. But the independent does know. So this controller is sitting here doing this calculation and it's calculating the CFM. Okay? Now, so we got that. But they have to figure out how much CFM is required in the space. We know how much CFM is going through the box, right? We don't know how much we need. What's the set point? So what we're going to do is, come over here. I promise it won't get any worse than this. So this is a calculation inside the controller. You don't have to worry about it. It's already in there and ready to go. This is another calculation. What it's kind of trying to do is come up with, well, how much CFM do I require? All right. Well, let's go back to 75 degrees. Room temperature is still the same stat. Still the same stat. That hasn't changed. But the difference now is, as the temperature goes up, the CFM is going to do what? It's going to go up with it. So let's put some numbers on this. 300, 1,000. So what the designer put together said was, when we're 75 degrees or below, I require 300 CFM as a minimum CFM. As the temperature goes up, I'm going to ask for more CFM approaching the maximum value of 1,000. Okay, so far on that? So let's take a look at this. Almost home free. Let's say currently the box is calculating we have 500 CFM going through this box. Okay? And let's just say for the moment that we're right about here, and let's say it says, I require 550 CFM because the room temperature, the load, as seen by that temperature, is doing what? It's saying, I need 550 CFM. He says, yeah, I've got 500. What's it going to do to the box? Yeah, you're going to open it or close it? Yes, I'm going to open it. Makes sense? Sure. It says, I got 500. I need 550 to open up the box. So here's the final thing. Let's say suddenly that main area no longer provides one as a static pressure, but three quarters of an inch. That number is going to go up, down. It's going to go down. So let's just say moments later, now it's saying we got 450 CFM. What's it going to do to the box now? Open it more. Pressure responds in seconds, not minutes. Okay, static pressure, any kind of pressure in the air handler, I think, is going to respond very, very quickly. So that means all that's too long. Can you still hear me a little bit? Or? I know he won't do it much longer. He likes to make noise. Well, okay. Sorry about that. So we're getting back into the response. So we now know that this air handler went down to 3/4 of an inch. We got less CFM. This he's going to respond right away. There's not going to be any lag at all. So that's why it's independent of flow fluctuations in the air handler. The dependent box says, hey, please, I'm relying on you to give me 1 inch. This one says, whatever you give me, I can adjust in seconds. That's why you do pressure dependent. Now, we're going to be playing around a little bit more with this a little bit later. That's the whole idea. Now, when we look at this will when I say takeaways, this is important. This number, that number, and that number. If nothing else, those are extremely important. That's why you want to have the tabs, when you're working with tabs checkout, that they are getting 300 CFM or getting 9,000 CFM. In other words, the scenario will go like this. You're in a room, you have to be in each area. There's a flow button, right? The gas person's there, you're doing the verification. And they're going to say, okay, drive the damper to minimum. And they'll go to each diffuser with the flow hood, and they'll add them all up. And that number at minimum should equal that. Okay? And then they're going to say, drive the damper full open. Do the same thing. The gas person will go around the room, they'll do a summation, and that number should be that. If it's not, you don't sign up on that room. Okay? Because that room was set up to have that design. Where do you think the max CFM value came from? Now, you didn't invent it, neither did I, but where did it come from? Invented, sure. But how do they get it? Load calculations. So they're saying, in order for us to take care of this load in this room, in the middle of July, we got to have this number. Or you're going to be getting hot calls. See what I'm getting at? So it's really important that you do this verification. Let me give you another scenario. When HVAC equipment is being designed, air handlers, chillers, boilers, all the like, how do they design it? They design it on design days, July and here, winter in Wisconsin. They design all of their equipment for design days. Right? So if you were to say, I want to get home and go fishing here. Yeah, we got enough air. That won't work. That will probably work during spring and fall, right? Because you're not at what? You're not at full load. But come your design days, that's when it's on the surface. So that's why you always want to verify. You're verifying for design days. Again, if you don't see that number, you don't sign off on it. You're saying to yourself, well, where do I get that number? Glad you said that. In your student notes, this would be found. It's called Gateway VAV Room Schedule tab. There's a couple of tabs over there. Good, that was fun. Yeah, much of it's 11 by 17 drawing one. So if you're getting sleepy, this is important. Don't fall asleep here. The rest of the stuff is up to you, but this is seriously very, very important. From your verification tab reports, this is really, really important. Give you a chance to take a look at it here. Okay, it's a room schedule. It's just a Excel spreadsheet. Perhaps person has a copy that controls them. You will have a copy. You should have a copy. That's documentation. You bring with you. And when you're doing verification, here's what you're going to do. You're going to go to each room. And here we are. The air handler that serves it, what floor you're on, and the room number. Then you come across this way. So let's just say you're in room 105. You want to verify room 105. So you come across here. So you come across from room 105. It tells us the kind of box we have. And then it tells us the unit size. And it says, here's my min CFM, and here's my maximum CFM. That's where you get your numbers. So, like I said, drive the damper full open, you're in room 105, and you should be seeing 150 CFM. Get the idea, and that's what you do for each and every room. If you do not see those numbers, it's not your job to fix it. We'll talk a little about how you can fix it. But that's what you're saying, well, we're done, well, schedule me to come back. You can't sign off on it, right? That's what's so important. That's why I said the takeaway is this number, and that number. So there's your min CFM, and there's your maximum CFM. You do it for each and every single room. So when you're doing your checkout, your verification, you don't do it from the head end. We're going to talk a little bit about head ends, but you do it in the room. I'll show you an example why in just a second. So far, so good. That's really a very, very important thing. That kind of documentation must be with you. Those of you who have been out in the field, are you getting the self-inspection? Are you getting things like this? Take those on the job. Yes, no, at least you're doing something. Good. Are you having trouble getting it? Sometimes I get some. It's a little hard to find it. When you go out, are you getting it? Or are they pretty good about doing that? Okay. Yeah, but this is something that you need to take with you. When we talk about the VA air handler, actually any piece of equipment, if you're going to verify, you need to have details. You need to have the tab reports. You need to have the drawings. You need to have information like this. It's really no point in showing up without it. If you were to tell me, hey, we're going to verify this, all the rooms in this college, if you don't give me this, I'm staying home. What's the point? I don't know what you want. I have no idea what the number should be. You get the idea. So that's why it's so important to have that documentation with you. So we're going to be dealing with pressure independent, and we're going to be dealing with wind schedules. Any questions on the difference between the two? Hopefully clarify something. All right, let's get that. All right. So, somebody gets the right idea. Hey, let's forget the sneaker verse stuff. Let's just go to the head end. We'll verify this one. We can hope quicker. Okay. Let me show you a scenario. Well, this window is here. What you're looking at is a piece of commissioning software that, in this case, is what Johnson Controls uses. Any vendor, controls vendor will have a similar. It's a commissioning tool. That's what they call it. What it is it's this laptop looking into that controller. So I'm a window into that controller. I'm looking at all the little numbers that are getting punched. Okay? So that's what I'm looking at. By the way, this says how much CFM is going through that box right now. Or that's what this controller is calculating. That's what we have right now. That's the number you would see at the head end. Okay, when they put the head end together and you're sitting wherever you're sitting, they're going to see that number, 179. You're going, hey, look at this. You're looking for 180, 179. Let's sign off on this window. Let's not bother going there. Need a volunteer. It's like that. Need a volunteer. Anybody. Don't be shy. Sure, please. Great. When you deal with this, I think your instructor probably did this yesterday. You push the IO button. You don't have to push the read button. And then we're going to come over here. And it doesn't come up, sometimes you gotta push the little red button. So what do you see? CFM. 80? 80. Thank you. It's only me. So she saw 80 CFM. Whatever, they're computers, they never make mistakes. Let's go with who says we got 180. Which one are you going to believe? The flow hood, of course. So now what I've done is I said, if you went to the head end, you'd say, we got what we needed. But we just saw the flow hood said, no, we got things here. That means in the spring, well, probably be okay. Not when it's 110 out there where we live. So you get the idea. I wanted to illustrate why you do not do verification tab or commissioning from the head end until everything is fixed. Once you verify this problem, and it's not you, but the tabs person fixes the problem, then you can use the head end amp. And I want to make sure you understood the process. If you always go room to room, piece of equipment, piece of equipment. Any questions on that? Okay, so what happened? Why am I saying I got 180 when we just said we got 80? All right, now I'm going to go a lot deeper, and you're going to get a chance to mess around these numbers. But more importantly, remember that room schedule. That's the big takeaway. So it's all very clear in your head. Let's find out why. What happened? What went wrong? So to get this calculated CFM, which is that number right there, the box controller is running this calculation. Did you touch on the stuff this week in class? Okay, good. So the box is running this. Well, we know that 4,005 is an airflow constant at sea level. It does change when you go up to higher elevations. Times the square root times feet squared. It's running this calculation to get what? CFM. We're not doing it. The little controller's doing it. But we know there's something wrong with that controller. Something's not coming out right. So we also know that from your discussion, that's feet per minute. Where feet per minute, like you're driving down in your car, you stick your hand out the window, that's velocity. That's not cubic feet because you're not encased with an area. It's just velocity. Feet per minute, how fast is the air moving across your hand. But we want cubic feet per minute. So if you take feet per minute times cubic times feet squared, you have cubic feet. Right? So we're looking at now is the square foot of this area right here. I want to know what that is. But we also know that 99.9% of the time, that's foot stuff. It's round. So we can convert round to square feet. And then this is where you can use a chart like this. You can say, well, what's the inlet right here, here, here? Okay, let's say it's 10 inches. That's the same thing as 0.545 square feet. So why is that important? Because remember that controller is using this calculation. There's only two inputs in software. The multiplier and the box area. Those are two different numbers. We're going to find out where they reside. So something got wrong. Something is wrong here right now. I got to have this number right and this number right. If I don't, garbage in is garbage out. That's the problem. In this case, it's the software issue. And they're going to be fixing this in the lab in just a moment. So you've got these two numbers you got to deal with. So you got to know the diameter of the input and then convert it or here. Otherwise, if you're deep, pi r squared divided by 144. There's 144 square inches in 1 square foot. That's what you want, square feet. And if you put 5 squared times this divided by 144, you get the same. But the point is, the input to this controller has to be verified. You got to make this adjustment. We want this sensor to read accurately. That's what we're doing right now. We're trying to get this calibrated. So we know we've got these two numbers right here we got to deal with. So far, anyway. But we do know, remember, keep your eye on the prize. We know we measured 80 CFM there, but this box says no, it's 180 CFM. We know we got a problem. The goal is, when we're done with our adjustment with this sensor, whatever you read with the hood, you'll match that number. Then and only then can you use the head. The whole idea is you have to go to each room with your room schedule and have it verified by the testers. Okay, anything so far on that one? Let's kind of go a little further here. So we got to figure out how to get this. So we now know this. So you would have to know the diameter of that thing. And let's say in this case, right there. In this case, this is the inlet to it. So what's this thing all about? All right, a couple of things. Every box manufacturer will have something called a multiplier or a pickup key. Those are different numbers. It used to be called a K factor. Somebody can agree on it. But anyway, it has a number associated. And the people who made this flow pickup has their own multiplier. Unfortunately, they're not standard. So if you go to Better Industries, or Carnes, or Johnson Controls, whoever made those, they're not going to say every 6-inch inlet is always going to have a multiplier. It's intrinsic in each and every flow. That's the challenge. So, why is it there? Well, let's go back to the drawing. A couple of things. First of all, we're dealing with velocity pressure at a very, very, very low level. And you're talking about, 0.01 inches static pressure. That's a small order for any sensor to get accurate. So what they do, another thing too is compounded by the fact that it's you've got total pressure going this way, right? That's the flow profile. You've got static pressure going this way. Static pressure, total pressure is stronger than static, so here's what happens. It ends up puts a little bit of a drag on the static pressure. So you've got these two issues. So to get around that, they multiply it. It could be 3.1. It could be 4.5. Each manufacturer will have to specify what it is. So they're saying, well, what comes out of here isn't the actual velocity pressure. It's been amplified a little bit. Now, not with electronics. It's strictly done how they machine the holes. Flow pickup. That's the idea. But they actually changed the value. So they multiplied it here. You got to divide it out over here, right? Because ultimately you want to get back to actual velocity pressure. So what happens is they multiply here, they divide it here, and you get the actual velocity pressure times 40,005 times feet squared. That's the whole long and short of why and how these work. So in lab, you're going to get a chance to actually play around with this multiplier. So far on that. There's a little bit of discussion. Just a little bit more, and then I'm going to get you folks into the lab here. Another discussion is fan assist. Okay. In other words, you could have a fan in that box, or you may not. It depends. Okay. So when you have a series fan, it's just what it implies. The main air is coming in like this, and in a series, right behind it, could be a fan. Now we do have one of those variations here. I'll show you what we want a series fan. The controller here, okay, that controller is controlling that fan. It's doing all kinds of stuff. It's doing those calculations. It's also going to control the fan, okay, if you have one. So the series fan is right behind the inlet air, and here's how it works. When you go occupied, well, how does this thing know that you are occupied? The head-end communication between the head-end system and the digital controller, as seen by, guys, on that wire right there. We'll talk about that a little bit later. That's part of that. So that head-end is communicating down through that wire into that controller. And it says, hey, it's 7 o'clock in the morning, start up. All the controllers going to go to occupied mode. Okay, so the time clock is not inside here. It's back to the pad. So it just said, hey, wake up, time to go. So this thing goes from unoccupied mode to occupied. When it goes occupied, the fan comes on and stays on all day. All day. It only turns off when you go unoccupied. So the head-end system comes down, that communication on that wire, and says, okay, we're going to the unoccupied mode. And then the fan will go off. But while you're occupied, it's going to be always running. So think of that, the series fan is almost like a booster. It's saying, okay, we're going to send out more air. We're going to help out the primary by boosting the hot discharge fan. And that would typically be a single phase motor, a small motor, and then a balancing motor to set down basically high speed. And they'll be a 5-star shooter. So that's what's going on with this. The long roll is going to handle that.
You're basically dividing this into 4 separate pieces.
Now,
You can't try to over that. So now this is but this happens all the time. You're to think about the architect doesn't get you in there. If you're doing a plan, I can't just what would be the
now you could have another plan.
I mean, the system sits right there. Yeah, basically,
It's possible you have something having parallel charges up. Exactly what it says.
yeah, we have
a main air coming out of here. We have a filter right next to it.
So
We're pulling in a kind of signal that will be back on this thing at the top. So you'd be taking a parallel thing over here. That's how the air coming in. Mix those air and send it out. That's a parallel thing. The idea is to use the plenum air, which is going to be warmer, right? During the winter season. So to try to get some more BTUs back in the cost. Because remember, these things, the main air gun has got what, 55-degree air right about here coming in. Roll contact. So here's how it works.
they have their own, they got their own. So, yeah, so this is an example of what happens with the annual construction the individual system. Okay.
This is going to be your damper. Let's say your winter set point at 72 degrees. Let's just say, for example. All right. What we're going to say is, when we get to 72 degrees and we drop below it, we're going to do that is do what? We're going to turn on that parallel fan. We're trying to get those free BTUs back. So somewhere around here, the damper is going to stay at minimum. It stays at minimum, whatever it is. So the damper's over here. We're going to say, okay, over here, the fan will go on. The idea, once again, is we're trying to get free BTUs from the pipe. That's how that works. So what it means is, it cycles. That's the big takeaway. Remember, the series fan, like I'm on, I'm staying on here. What we're going to say here is, no, we're on, but when we get up over here, I'm going to go off. So it cycles all day long. Makes sense? Again, the controller is taking care of all of that. Here's a schematic drawing. This is a control flow drawing right here. So here we're showing that we have a VAV box, single duct, pressure independent. Right, we got that going. And we've got a reheat, in this case, and we have baseboard. Okay, so let's talk about that. I want to focus in on the reheats, basically. If we take a look at a building, looking straight down the school, it's basically, you're going to have interior zones, right? You're going to have exterior zones. Let's just say this is in Wisconsin, okay? And we got that outside air surrounding it, right? What's going to happen here is this. It depends on how severe, how cold it is. In northern Minnesota, it could be minus 50, who knows? Northern, Wisconsin. You could have a really, really cold temperature. Let's just say you've got minus 15 degrees out outside. Over a nice winter day. They could have something like this. So they're going to have perimeter heat. So what we're going to say is when we get below this value, let's say right here, we're going to turn on baseboard. But right now we're saying, hey, we're going to try to get the free BTUs, whatever's in the room. It's not working. It's too much of a load in this area, exterior. So we're going to turn on baseboard. Then you're going to have your hot water coming in and putting up a blanket of heat, right? Along each wall. Okay. Not only this, so that heat is there just to go up with a blanket of heat, right? It helps the room a little bit. It's also there for not only a blanket of heat, it also keeps what? Windows from frosting up. Remember, minus 15, the surface of that, what do you think the dew point is? It's real low. It's going to be real easy to condensate the form. The idea is we're going to elevate that dew point, right, by putting up a blanket of heat. So it's got two purposes. So the controller says, okay, I'll start to open up these valves. As the temperature goes down, I'm going to start to open up the valves to allow more hot water. See how that's going to work? Now the sequence may or may not, depends. In this case, we've got a reheat right here. We've got another valve that's going to be activated. All being done by this controller right here. So the controller says, okay, we still can't get the room, still not where it should be. They kick in the reheats. So now these dampers are wide open, and now we're going to start opening up that valve right there. Make sense on that one? That's what we're going to be doing. Now, you can have reheat followed by baseboard. That's strictly up to the customer what you want to do. You want to sequence your reheats first, followed by baseboard. That's easy enough to do. The controller can do either one. That makes sense. So now we can address all those issues. Now the reheats themselves. Here we got one that says fan assist. Down here, well, in this area, reheats at best would be a stage of electrical reheat. We don't, in the valley, we don't have a lot of falls because we don't get that cold. However, when you go into the mountains, 2 hours severe, it could be 5,000 feet, 6,000, 7,000 feet. They get winter up there. So right now, it's cold, Flagstaff, or Pine Top, and there's other issues. So they can have this. But either way, what we're saying is instead of having hot water, we're going to have electric reheat. So then you have so many stages, maybe each one is 1 kW. And what will happen is the controller will stage them on. So instead of using hot water. Anything so far on that? All right. Now, before we get to the lab, this is a nice checkoff list. Okay. These are the kinds of questions that you want to ask in each zone. Okay. Give you a chance to write it. Practice here somewhere. Should say verification. Okay, functional checkoff list for the VAV boxes. Here's some of the basic questions that you want to take a look at. Okay, what kind of diffuser has it been connected up properly? You use it right here. Does the maximum CFM actually required? That's a really important takeaway. Is the minimum CFM actually what's required? Those are really important. Do you have, when you have a call for heating, right here, there might be a different minimum CFM. It'll be like room schedule. Has that been looked at? Just kind of see what I'm doing. Write down a little checklist. Right down through here. Do you have the proper static pressure? We're measuring that. You need to know what's our static pressure. I see right here. Have they been recorded? You kind of get the idea. Is everything that verifies static pressure pickups? Have they been also calibrated right? So everything I've been talking about is kind of capsulized right here as far as what you need to see. So if nothing else, you can use this as a little cheat sheet verification list when you go out. Questions so far? All right, now let's get ourselves in the lab. So what we'll do is, I'll break it down this way. There's a group here, there's a group here, and we're going to do a couple of labs. So all of you are going to do the labs. Just going to have to switch them off. Here's the lab right here. What you're going to do is each one of these diffusers has got a label. 103, 102, 101. And I want you to write down the CFM that you measured. And the temperature will also be on the flow rate. You can get both. So you're going to fill out this little chart and then add everything up. Okay. You'll be going up and down this corridor right here. Also, while you're doing that, you're going to fill out this table. You're going to fill out room 101, which is down there. Is it a single duct, dual duct, fans? Fill it out right here. Is it pneumatically controlled, visually controlled? Is it dependent or independent? You're going to do that for each and every room. Again, you'll be walking up and down this corridor right here. So that could be one group, I don't care. But you're going to have swap. So you can work out how you want to do that. Now, the other thing is, oh yeah, remember that room schedule you have in your handouts? You're going to use that to fill out 302, 3, 4. You don't have to go to those boxes, just use the room schedule to fill out this data. K factor is the multiplier. So then you're going to fill this out using that 11 by 17. That's the first part of your labs. And the second part, you're going to use the room schedule again, the first one that document, and you're going to locate these values right here, the cooling min and the cooling max flow separator. So room 102, that's the one that this laptop is connected to. Okay? And then write down the cooling min, cooling max flow. Then you're going to change in here, you're going to browse to find those values. I'll show you when you get over here, I'll guide you through this one. Finally, the multiplier. Remember I told you how that can greatly impact what actually is being calculated. Actually, you can start right at step 3. So in other words, start right there. We're dealing with this VAV box, that diffuser, right? And that's the inlet. The inlet to that box is 6-inch inlet. So you need to figure out what is the area in square feet and write that down. Okay. Then you're going to enter this value. Okay. How do we do that? Well, we're going to go back over here. You're going to be dealing with this window right here. So whatever you calculated, we're going to change this number. So how do you do it? Real simple. Just click on it, enter whatever value you have, and select override. You have now made a change in the software. You're recalibrating that sensor. That value then will be reflected right there. Next, wait a few minutes, and then use the flow hood. Okay? And measure the CFM right here with the flow hood. I'll let you folks do that. Write that down. Okay, there's the flow hood. Next thing you do is you select the input button, and you get to supply differential pressure. Well, where do I get that? Right there. Whatever that is, you write that down. Put that value down. Okay. You're almost there. So, then you come back and say, all right, I got all the numbers I need. My full coefficient is 4,005, right? We're talking about that. So 4,005 times the area. Calculated an area. Put that number in here. What did you measure with the flow hood? You divide this into this, once you get the square, I think you get the square. Then, once you get that, what you supply delta T. In other words, what did you measure right here? Okay. You put that down here, and you got a new pickup gain. Almost there. Now that you got the pickup gain, you come right here. You can do that number. You override. Again, wait 2 or maybe 2 minutes. Give the box a chance to settle out. What should happen is, now you're going to hit the flow hood one more time, measure here. And that should equal that number right there. Then you're done calibrating. So you went through the whole process. Questions? Tell you what, let me move this out of the way. Okay, let's well, we have safety glasses now. We're going to be in the lab area, so you need to get these on. Make sure you got your safety glasses. I don't care what group. You got 2 groups. If you guys want to do the first 2 labs walking up and down here, then this group will do the little lab procedure I just went through. When you're done, you're going to swap, so everyone's going to get a chance. So I'll get you folks started over here. Once again, when you're using the flow hood, you only have to do the IO button, and if it doesn't read, call me over. But don't push the read button or anything else, just do the IO button. Yeah, let's get you folks going here. See if you guys, please. You're going to be working up and down this corridor, filling out those tables. And then the other folks are going to be working on that laptop. When you're done, swap over. Yeah. You want to start at 105? Yeah. Okay, for the folks who are working over here, you can use my laptop. So you've got, for you folks who are going to be doing this lab right here, it's got the adjusting the pickup gain, which is on page 12. And again, what you're going to be changing is this number and that number. And you're going to keep your eye on that number. That's what's being calculated. That's what he thinks is coming out of that diffuser. Using the two numbers, you're going to make changes. Leave you to it. Talk and yeah, you can use my little goofy calculator. Use your phone, whatever you want to use. I'll let you guys do that, and that's about it. I'll get going. Squared, right? 44.
Oh, yeah. Hey, I went up there a little table.
Oh, I just went up to you.
Yeah, we did it by 144. They have one a little earlier. Oh, it tells you like different sizes. 6. Square. Oh, not a square. Switch.
Yeah, you know, and you're fine.
Yeah, you got it. Absolutely. Yeah. Mm-hmm. Incidental.
Yeah.
I would wait a few minutes and have measure. Basically wait till it starts kind of evening out.
We did like 6 off of that.
So easy.
Yeah,
I saw it.
Oh.
Yeah, that's why I do the
You got it.
I'm perfect.
Yeah.
So then you're already gonna go.
We have to 196. So we gotta wait for the door. You have to.
Yeah. Well, worst case. That should be.
Yes, sir. Nope. It's now, it's a small box. That little box is there. Yeah. The box right here is that small. There's no fan. That's what they call a cooling only box. So, but down at the end of the array over where a gym is a big one. That's what I think. As a matter of fact, yeah. Well, question, Dave. Oh, you're waiting for the, okay, I think they're coming. Yeah, we're good. So whenever you're done, you guys, did you get to work and everything?
No, yeah. We're waiting.
Oh, okay, yeah, good, good. Yeah. Stuff's in the right now. And you're gonna run your calculation. You go. You do it. You do a little, like that. And keep that up there.
Yeah, I think that's like in the button on the software. Yeah, that, it's spirally on that. It's not that sense of
Oh, yeah.
It's for this, right?
Now, that's one or two.
yeah, I believe so. It's the software. I mean, I think like the restrictions and everything are going to shift. Yeah, that's going to shift all the pressure.
What, 2, 3? That's good. Done. What coefficient is that 4,000 number, right? 4,005. Mine's the area. My flow was 03.
That's that 4,005 one.
No. 105? 105.
I got 3.4. Figure it again. Photo and shit. 4,005.
Let's
Without the butter, and then quarter square. Yeah, so what else I did that divided by 3. That square. And I multiplied it by delta P over 20.
Can't use it in structure.
Yeah.
I'm used to talking for PM and this thing.
Yeah, well, so I think somewhere in there. Right. Square that. No, I mean, square it. Yeah, no, it's, I think it's what do you need? See, I think you might have square that. And then multiply by 40 times. And it'll be a little bit because I think you took your area to an additional. But I mean, it's close enough. 3.4. I got 3.4. That works? 3.48. Yeah, I mean, at that point, it's not good. I called the question and how accurate the flow of it is. Pressure sensor. So we have that, now we're going to plug that in, and he's plugging it in right now. Yeah, it is. And then I think we wait again. I think we're going to sound wait till this kind of comes out.
The plastic that's in this because he's thinking he's got no flash on it. I'm going to have to do it. Scott doesn't do it. Scott.
Yeah, I have a question.
Well, off in the back.
Second. So at this point, it's not scheduled even for the city of College, they'll be in the process.
Well, and you know, the other possibility is, oh, yeah, right. Like going to the beer access.
Yeah, basically, there's a close door that's reading. Yeah, no, it's reading at 179 or something. Yeah, and then yeah, and it's definitely covered in that for closed, definitely. The only one that says it's scheduled to be pumping out 180. And it's reading 179. We're getting 180. And then it said it should be within 5%. And then basically put it all back.
It'd be pretty tough to do. Yeah, because it looks good. Put it back.
No, it just resetting it for the next house.
Yeah, because then you're my first
Or you do one or two.
You want to hear that one? I was at the end. I was just putting it back to where it for the next one. I think we got everything we needed, right? And then now we can start on this one. It's going around reading.
And I looked at my first best guess. Over that I had 5.5 hours. It takes some time out here. And I track it.
Is this
Diagnostic code.
I was looking up what it set point on.
You guys reset the computer, yeah, BBC.
I believe you reset it, right?
Yeah.
Yes.
Yeah, it's outside 5%. I was going off the 180 and but that's not in this. That's in the set. Yeah, I think someone might have. I want to know if it should have been 180 or it didn't tell us to change it.
Yeah.
It was within the error comment. Now, you guys, is this set point for 180?
No, yeah, the set point's 180. You want one more look at that one.
The schedule it says it should be 230.
Okay, you can change that.
I wasn't, no, I mean, we already did it. And it's within 8% of this. But it's definitely not within 8% of 230.
Okay, it might be the air handler.
So it's because like if it tells you set that.
No, that's good.
Yeah.
Good, okay, then you folks give the other one and go all the way down the corner, and then you folks come on over here, which I don't give you the other work.
I've already reset.
Oh, you did, okay, great, great. Okay, So now you folks work on here. Then you guys go over
It's
here.
also just trying to understand what we're doing.
It's supposed to be within 5% of what this.
Not the schedule.
Yeah, and the schedule supposed to be then plugged into this. So someone's changed that.
Oh, I got you. That's what I'm going.
The
Now,
error on the system.
I guess right there, yeah, basically, again, the process variable should be equal in 5% of the load. But you did your business. It might not take enough air, but it's schedule. At least you know everything. Make sense? So we're just gonna say that we'll live with 180 as the settlement.
Even though schedule says two.
Yeah, what's the other say? And, yeah, so
in
now-
actual field, with the schedule that you have should match the set point in. Yeah.
Okay.
In the field, yeah, you want whatever the system set point is on the schedule.
Yeah. And you guys will want it all this order, and then you put one over here, and you're gonna be changing that number, and you gotta keep your eye on that. This is your CFA. That's the one. Oh, when you're done, that number should equal. So you're gonna be changing that number and that number, and you're gonna there's a multiply.
That earlier, we were supposed to be running on 6, right? 6 inch. Yeah, we went back to the chart.
Yeah. Yeah.
How's that what we're doing?
Well, back up, because you still got those little two and two, but you gotta get those from
Using the oh, so I got that off the little sheet that they always got. So we got 80 and 250 on that.
Okay, so we got, so next we got one more, so make sure that we have to put that. Just send me the one, send me the one.
Yeah, it's on the plate. It's on.
Oh, all right.
So
Okay, so we gotta go 8.
6
that's your set point. Like, you change that.
Well, what happens is
The box has an area of 196. Where's the box? What's on the parameters? Supply of fuel.
6 inch and let it go. 196.
Probably about 196.
So that's so I have to try to use some papers. Oh, you can't. You don't have to. Hold up. Yeah, hold up. Because you're going to say, well, that's what that was the same one. That area is like 535. You change that now back to yes. Wait for a second.
You had to look at
Yeah.
Oh, okay. I'm about to say, did it change?
So instead of like electric motor, it's a compressor airline, so not used for
Yeah. Hold on, guys. Okay. Click on inputs right here.
Input?
Okay. Yeah. Click on inputs. Okay. That's your supply delta T right there. You override that, just take that value. And right now,
Yeah, that's what I was asking you to do now.
You gotta measure the air.
Okay, yeah, measure the airflow. There you go.
Ah, okay.
I think a lot of stuff here is done more just so you have access to it.
So now you want to bring this value, you want to bring this window down, I'll show you real quick. You want to do, now this, you got that, now you're going to change that. Okay, so that's, okay, that's a multiplier. To the processor, so you got everything you need right there. So what did you get for CFM?
246.
All right, and then the differential pressure is right there. So then you just value right there.
E2.
Now you're ready to crunch some numbers.
What would like obviously be different on like electric from visual? Is there visual?
First thing is going to be this is a cooling only box, so it's going to be a quarter box. So I'll show
Right
you.
here, it's 246. Let all you fast snap. box.
What you got now?
This is what I did.
You squared that?
So,
And the supply delta is 0.32? So what do we do? 2.258?
up here, this is the ratio. Now we have the recording. Put it on here.
$2.258 is what you got. Or we can do a 3.3, right? Does it matter?
I did 3.25. Oh, right.
No, you
Is
did.
that what you got? Is that?
You see,
Yeah. Wait a few minutes and we need to fill it in, write down the slip.
so now that you change. This yet?
Yeah.
Okay. All right, now, get your fill hood. And the fill hood should equal that, so you're gonna be right over
Within
here.
5%.
Yeah, within 5%. What's the FM? I see you're there. Good job, good job, good job. All right, you got that, let these other guys finish up their line, and then we'll do a review.
247 is what we got.
Good job, excellent. Let me fix it. 3.35. Yeah, I'll set everything back, yeah. So go ahead and do that, and let these folks finish up, and then, we'll definitely do a review.
Good job years ago. We had a bunch of linears in the building. My tag actually on the rectangular hood, on the square hood and stuff. What are you doing? Oh, I just read this. I'm just taking it and getting mad. Get off my job.
You never know what you're gonna get.
Too lazy to go to the box and get the linear hood out. I mean, it's there. He's already got the stuff. Yeah, she's too lazy to do it. So next thing I know, he's made up this cardboard contraption that he's going to try to make.
You know, and that's why you're there. And you're exactly what this whole school is about. Guys like you show up and know what they're doing, and know what they have. And you catch these, not every contractor, I'm not gonna say that, but there are some. And they're like, hey, no, this is acceptable.
I have an admission that I've worked more in the last 5 years. I care to ever know about HVAC. Last 5 projects I've had, that's basically all what we've had. It's remodel jobs. So we've been doing variable frequent flow systems and band-aid systems, VAVs, and heat boilers, and real learning.
Are you guys, the next commissioning class, they're gonna have their refrigerant flow. Are you seeing a lot more of those going on?
At Dietrich, where I was at, yeah, I had done 3 before I left.
Okay.
2 complete restorations and 1 was a partial. We did it's a small portion of the building. The first one was a nightmare because the systems were just coming out. The contractor used the first one he had ever done. He tried to use crimp-on fittings. It didn't stick. It leaked out the wrong tube. We had warranty issues out the wrong tube. They had problems from Mitsubishi with the transition couplings. The only way we found it, the problem with the systems are that it's peaks. when you got to keep pulling the PP is when you find out, because some of the refrigerant had leaked out, but you had no idea how much it did. The only way to know is you're going to cycle the whole system down, draw every bit of it out, measure it, weigh it, figure out how much was supposed to be in there, and then go put it all back in. The only way we knew we had leaks is because we were starting to see refrigerant or oil drips on the ceiling from where the box was. So the last system I did went extremely well. It was brazed, the braze system, did all the brazing with nitrogen in the system. Everything was tested to max potential. Crazy number. And then pull back and it took forever to get the system back. It was like you got 2 miles of refrigerant. The small stuff, but still is everywhere. But we don't like them because we have no control over the controls. It's just getting to the point where they give you 4 or 5 items that you can monitor. You can't even make changes. I'm pretty sure Army's going to go with the Air Force and say no. We can't use it. The other issue we had was they're not made in the U.S. So most of these smaller projects, we had to go back and get variances from contracting because couldn't meet the Buy USA. Right. And then the other side of it was they weren't doing the ash rate calculations for concentrating refrigerant. And the only way we finally got this job to go was we had to get the system. We had to keep the LS system running all the time to guarantee that we weren't going to have a possible leak and we had concentrate levels of refrigerant.
How you guys doing here? A couple of minutes, we'll wrap up. All right, let's do a review. What do you get for total CF now? 570. How about you folks? How much? Okay. Yeah. Now the next table. 101. Tell me about that. Option 101. Single duct, dual duct fans. What else? Independent and pneumatic. Yeah, it's pneumatic. 102. That's one you're working on here. Tell me about it. About room 103. 104 though. What about it? But it's got a Series fan. Is there any reheats in it? Series?
No.
No, it's a series fan.
Instead of parallel, looking at the box.
That's right. And any reheats? Yeah, and 104. No reheats on that. No reheats. It's strictly the series fan. When you look on the other side of that box, the VAV box, there is a power inlet, but there's a speed control for that. That's not for electric reheat, that's just for the fan. So medium low, medium high. 105. What do you put? 105. Okay, so look at the PVC. You've got some back and forth stuff on that. Okay, yeah, you don't have a laptop right now. Yeah, it's for the monitor. Good. I want to ask you had no trouble using the room schedule, any problems getting that data? What's that? That's really easy.
Yeah,
My question was,
I think I kind of did it
I need to like
when I was sitting there before we started.
good. Anything else? Well, thank you. Want to get some great and then go to your next station. Hope to see you tomorrow.
It's like it's an exercise in reading it. I think we're what time is the next one start? Yeah, I look at my schedule on the other things.
10. Maybe a 10-minute break.
Yeah.
This, it's like, this is just flex.
Yeah,
it is, right? It's not, it's not, it's not, nothing in there.
No, and they still made a nice transition. The idea is wanting that down. Yeah, it's just. We get some water here. Actually, the quarter's got.
Wow.
Yeah, you can look there. They have a.
Sure. Yeah.
School here is outside.
Easy. Yeah, it is. I have the tickets. Here.
All right. You have 7 or 8 people there? I need, okay, we'll give it a little more. Just in time delivery. Same low price. Well, all right, we're all here ready to go. Welcome to the VAV terminal box. That's what we're going to be dealing with. Tomorrow we'll be dealing with the VAV air handler. That's going to be our schedule today. I'm Dave Kenny. Please just call me Dave. I'm retired. Johnson Controls, 32 years. I'm an adjunct here at college, so that's all I want to do is accommodate. So anyway, you got your student notes. That's yours to keep. If you opt to come back to the air handler, we'll just look with you. It's got both the VAV box and the VAV air handler. Before we get into the book itself, I always have to get around and get to know you. Your name, your title, but what do you really do each day? Because your title is just how you get paid, right? We all know that. But what does your boss really have to do? Are you in the field a lot? Are you in the office a lot? And just give me a little heads up on that. So,
John and I have trouble with there's a few ways half the day out in the field, on the power, and the other half is doing the steel
I'm Chad Crosby. I'm the Police District. I'm the HPA Civil Design Engineer.
Oh.
I do design and
okay, so you're in the office and the field.
yeah, I'm on the field much because we win the
You
release.
do design.
We'll stay in the office.
Okay, good.
David Rex. I'm the VA intern right now. I'm a mechanical engineer, so I'm on a lot of rotations. Haven't really settled into any capacity yet.
Okay.
Kevin Clark, I work for St. Louis District. I am also the QA and the senior water, so 9 is split, about 50-50.
Tristan A. I'm the district.
So you're in the office more than you're in the field. Okay. That's right. Great. What I'm going to do is we'll definitely get into some things like how things work, but primarily my focus is going to be you're at the site and you're going to do some verification. All right, and you're going to keep all its contractors honest in this case, tabs, and that would involve some controls people in this case as well. So that's how I'm going to kind of treat it. That's my focus. So we'll get from that. Open up your student notebook and hold on a second here. And let's get to this this first page, which is the structure guide, don't worry about that. It should be like VAV terminal units and VAV performance objectives. So why don't you find that page while you're doing that? You get a VAV box. Okay, the first thing I want to do is just quickly go over the objectives. In particular, this item right here, the VAV terminal box. So we're going to be looking at this area right here. Part of it will be using this laptop. You'll be dealing with some software, adjusting VAV box parameters, sensors, things like that. We'll be doing some of that. Beginning into different types of VAV boxes, I want to do a little review, which you learned this week. Getting into that. Fan assist, we're going to talk about that. Any kind of reheats, I want to chat about that as well. You'll be going through this lab, investigating some of these boxes, so you get a chance to investigate those. Yeah, big one here, room schedule. What is it? Why do you have to have it when you're out finishing or verification or any task or finishing? What is on that schedule? Why is it important? We'll talk about that as well. And that's about it. Yeah, I think that's about it. We'll definitely cover those items. Page 2, we're coming in a different, pretty in the same section. So we're talking about the inlet to a VAV box, which here we've got a variable air volume box right here. The inlet is right there. This is the drop off from the main air handler. And the diffuser's right there. So what we're looking at is right there is the inlet. That air handler back there, which is we're going to get into tomorrow, is providing the static pressure and the CFM. We call it CFM. Very typical, 55-degree air coming in from the air handler, and it remains constant pretty much all year round. We'll get into more of that discussion tomorrow. And in this case, one is a static. So we see the water column is static pressure, not velocity, it's static pressure. So we're going to be looking at the inlet of the box, which is right there, pushing that air out. Being metered by a damper, just like you saw, I'm sure, this week. The damper right there, all bumps happen. All we're going to be doing is metering the air. That's all we're going to be doing, depending on the load in the room. Of course, in this case, you're going to have multiple diffusers, right? So if you pull back the ceiling tile, you're going to see all your fresh stuff coming off this box being distributed out. When you're out in your test and balance situation, what you're going to really want to do is have the task person take the flow hood and measure each one of these diffusers and add up their values. They're going to compare it to some design criteria. So that's simple. But it's got to be done. I'll illustrate why you have to do it. So that's basically what we're going to be doing. In this case, it's a lab, and we only have one diffuser because we're landlocked in a big room. So we're just going to be doing one diffuser. Well, any questions, please ask. Raise your hand. If I don't have an answer, I will get you an answer before you leave, or one of you will come up with the answer. We'll make sure that you got all the answers. So don't be shy. That being said, let's move on. Two different styles of VAV boxes, thermal units, pressure dependent and pressure independent. What they both have in common is you can have single duct, that one. You can have dual duct. Not too common these days. The big old air handlers used to be pushing out a hot deck and cold deck. So like you might have two inlets, one's got 90-degree air, the other one's got like 55-degree air. All you're doing is mixing. That's all you're doing at the box. You don't see a lot of that year round, but it's not as prevalent as single duct. Both of them can do reheats, whether they be baseboard or they're actual reheats in the box itself, electric or hot water. The big difference is heat kind of is independent. From your discussion with your suite, what do you know about the difference? Are they the same? Is there a recommendation about one over the others? What do you guys think? Independent box versus independent. Now we're talking about how the strategy is to move that air. Let's talk about that. On the next page,
In front of the VAV, they're independent.
okay. So you learned about independent, but if you talk about independent, well, just curious. Let's go through it. It's not a big deal. So here's what we're going to do. Next, we've got the room temperature as seen by standard old stat. That's an input into the controller. So we're going to travel along that line. Over here is going to be, say, 75 degrees set point. We'll talk more about when that number comes. That's what we're trying to achieve in that room. While you're occupied, you're going to position the damper from minimum to maximum. And this is in percent. Okay. So how much are you going to open up? So if the temperature goes up, yeah, just open up. We're talking about a dependent box right now. Okay. You're saying, hey, well, that's good. It's getting hot. Open up the damper to that 55-degree air coming from the air handler. What's wrong with that? A couple of things we got to talk about. First of all, let's go back to the stat. The time constant on how fast it reacts is very different from pressure. When you're in that classroom that you're in, or a big auditorium, whatever, how fast do you think it takes? How long do you think it takes to change 1 degree Fahrenheit? 5 seconds? 10 seconds? 1 minute? 5 minutes? Yeah, you could be up to 5 minutes for a big, depending on load, right? It could be. It's not a problem with the sensor. That's not the issue. It's just the nature of room temperature, how fast it changes, and where they place that sensor. So you got a slow response. Okay? The other thing is this. I'm a salesman. I say, hey, if you buy my box, so long as you give me 1 inch of static in here, I'll give you 1,000 CFM running out when that thing is wide open. If you don't give me 1 inch of static, I'll bet you off the ground. I can't tell you what's going on in that box. Kind of get the picture now. With a dependent box, this controller says, I have no idea how much CFM is going through. It's not a clue. I have no idea what the pressure is. I have no clue. I only move when that room temperature changes. Therefore, I'm dependent on the air handler to provide that one. Makes sense, right? So you got to make sure you give me that 1 inch because I don't know what's going to happen. I can't respond quickly. Yes, I'll respond eventually if the temperature goes up, but I'm going to be lagging big time. See how that works out? That's why you don't want to have anything. You know before what's on the next one. That's why you don't want to. If you're in a, someplace that's not critical, say location area, what we got, maybe a dependent box would be fine. Like if it's doors opening and closing, that's not a critical area. But not office buildings and other places. So you get the idea how that would work. So we're not going to use dependent boxes. Now you know basically. So how do we get around this problem? I'm going to use this guy here. The first thing to notice about a pressure independent box is you got a flow pickup. This flow pickup is nothing more than a repackaged PO2. That's all it is. PO2 repackaged. It's not going to be in the box. Now in the real world, of course, you can't be looking in. You will see these. Right away, you know that this is an independent box. So that box there, that dependent or independent, those are close enough you see it. What is this box? Is this box an independent or dependent? Independent. That's two boxes. That's right. That's an independent box, which is what you want. So let's get another picture. Total pressure is made up of static, right? Plus velocity. Okay, that's what it is. So the impact pressure that's coming, hitting the front of this face right here is total pressure. Right? Now, for your expressions, what is static pressure? This pressure that pushes out of all angles, right? It's called the bursting pressure for good reason. But it's pushing out. That's your potential. To what? To move air. The result is we got static pressure, and we're going to have flow. Right? See how that. Okay, so where are we going with this? Well, that means if you take the total pressure minus static, you've got what velocity? I've got static pressure, I got total pressure. What I have out here is velocity pressure. We're not there yet, but we're getting there. Follow me so far, any questions on that? So that means you've got two hoses, one here and one here. This would be the high side, this would be the low side. The total pressure, which is the static pressure, as measured by that flow pickup. So now, we'll do the scenario. Here's what happens. Inside the controller, it's going to run a calculation. We'll talk about that a little bit later. He can extrapolate that variable velocity pressure and convert it into CFM. Now, this box controller knows how much air is going through it. It's measuring. Remember the dependent box, it didn't have a clue, right? This one does. So it's now calculating calculated CFM. We'll talk about the calculation. So far, so good on that one. Okay, so it says, okay, I've got 500 CFM. Okay, right now I got 500 CFM going through this box. Well, what he's missing is what? This is the set point. Well, what do I need? Okay, so there's another little calculation going on. On the y-axis, we're going to have a calculated CFM set point. This little calculation is actually coming up with what do we need for CFM based upon what? Our load. Well, what's the load? The room temperature. That's the load, right? Everything's on load. So we're gonna say we're gonna go from a minimum CFM to a max. This is only coming up with a 7. So let's put some numbers on that. 300 and 1,000. So at 75 degrees in the room or below, I'm going to go to minimum CFM. When I go above, I'm going to start to increase the required CFM. Okay. So what happens is this. Let's say it's somewhere around here, and it says what I currently require is 450 CFM. This thing says, well, I got 500. So what's the damper going to do? Open up or close it down? Pitch down. Because it says, hey, I've got 500 CFM. I only need 450. So it's going to sit there and pitch down. Okay, let's change that a little bit. Let's say, for the moment, it requires 550 CFM. Still measuring 500. What's it going to do now to the damper? Open up or pitch down? Like to open up. Yeah, sure, to open up. Okay. All of a sudden, the air handler has a problem. The air handler starts putting out 3/4 of an inch static pressure. This number is going to do what? It's going down. So let's just say it drops to 450. It doesn't have 1 inch static pressure. Now it says 450. What's it going to do now? Once 550, it's going to open up more. Get the idea. Static pressure, or pressure in general, changes in seconds, not minutes. It's very, very fast. It's got a very fast time. It reacts very, very quickly. Therefore, it's going to make the changes very, very quickly and adapt to it. Therefore, it's independent of flow fluctuations of the air. That's the whole story. That's the initial whole thing with the electrical. So it's independent. Regardless of what the air handler does, in seconds, this can respond correctly. So that's why we always want to bring it together. That makes sense?
Understanding the industry, both that
oh, yeah. The point's well taken. Mechanically, we haven't solved the problem at all. We just said, we have to open up. You're right. Then we're going to get all the CFM required. You can still get a hot ball. Oh, yeah. I'm just saying, this part of the circuit, though, will respond to your pattern. Hopefully, it'll correct itself downstream. It could be a damper, it could be a balancing damper that's stuck or insulation for the guy to fall through. But he's right. I didn't say we're going to get the required CFM, but I will say we'll do the best we can. And that's an interesting point. That's where head ends can help. Because now you're saying, hey, that room is supposed to be 75, it's 79, now get hot balls. Now they can start to think about, now they can start looking at head ends, where's the problem? And then now you can say, well, we know the box is open, so I don't have to worry about that. And I start looking for the system again. Why is it going on? Absolutely right. That's a good point. So far, so good on that. So that's the difference between it, and that's how these two work together. Now, if you're getting sleepy, wake up a little bit longer. Because what's important here? What's the takeaway? That number, that number, that number. We're going to talk about where you get those numbers are very, very, very important. So in other words, you're in room, whatever room you're in, 102. You're going to have what's called a room schedule. Take a look at it. You're standing there next to your, with someone else maybe helping you verify this. You tell the contractor, tax person, to go to name of position. They'll go to each diffuser. They'll add up the values and shoot you for that number. That's what you're looking for. Then you're going to say, okay, drive the damper wide open. Okay? Okay, you drive the damper wire with the same thing, do a serration, diffusers. You get that number. If you don't, you don't sign off on it. Okay, the schedule will come back in. We're not getting any cards yet. Right, gotta make sure we do something for that. That's probably the most important thing. Also, are you getting your real temperature? So far, so good. Yes, sir.
Does it ever fully? You ever get a call with what they designed, what they should do, it's just
Oh, yeah, you never close all the way.
no. Does it have a capability?
Well, the controller could. Could you go all the way down and close off? Oh, yeah, the controller could do that. In fact, sometimes there's an auto calculation algorithm inside this self-calibrate itself. And it will close all the way to make that adjustment. But good point. That's a real good point. While you're occupied, do you ever close that thing? Yeah, you can. Fine. Right? So put it, sure, box will do whatever you tell it to do. Yeah, absolutely. But of course, not while you're occupied. When you're unoccupied, sure, you can close that off. I can think of maybe a fire situation, a smoke situation, they might have the boxes go to your own divisions. I remember all garbage filters, we got 20 bucks that face yeah, right here. Yeah. Oh, sure. That's fine. That's the control of what's going in that position. That would have to be verified. That's a verification. For you, it's a little extra step. Well, it says here.
Before we take over, we'll make
Sure, sure. So that's whatever is required. But for the basic simplest thing is in the max, and you can't ever close the box off. So when we look at this number here, what if you go like this? It's springtime. You're going, I want to get out of here. Look at airflow. Okay. It's pretty comfortable in this room. Okay. The problem is, yeah, spring and fall, that might work, actually. Not on a design day. Right? There's a lot of engineers here. How do they define this number right here? Where did that number come from? It could be 1,000, 2,000. How's that derived? Yeah, it's on your load. Your load is. How many BTUs? 500, 500, 500, 500, 700. 3.4 BTUs per watt, right? All that's factored in to define what? The ultimate load, which is BTUs. From BTUs, they get that. It only lasts about a minute. Not much we can do with it. Exercise. Boy, I can never get a balance of people all cold. Heat. Trust me. Got a funny story. When I was dating my wife and everybody, we were at the Master by that time. Had my son-in-law show up. He's living in Wisconsin, so I said, "Hey, Keith, bring the trailer to the house." And I was surprised. He pulls up. And as he pulls into the driveway, my snowblower and my lawnmower. I said, "I'll never see these again." And then he scarf goes up. Snowblowers are expensive. Yeah. You don't have to show the being an old man, I'm going, I don't want to do this crap anymore. So anyway, back to these values. So you can get an idea that this is a critical number. You have to get that airflow because when it's 110 out for 3 months here, oh yeah, you got to make sure you have the design flow or you're not going to get unplugged. That's why But as you guys, a lot of engineers know, you design on what? Design days. How do you design how many boilers and heaters you need in your space? You're living in Fargo, North Dakota. Where? Design days. What's your design day? What's my outside air? What's my delta T between the roof and that outside air? That's where it all starts. How many BTUs you need to put in that room? Design day. What is it? It's different. It'll be different for those people versus down here. So that's why it's so critical that these companies get done. And if they don't get them, then you say, schedule me for that. So that's really your biggest takeaway. Your set point, min, max speed up there. Make sense on that? Let's take a look at the room schedule. This should be the tab. It's actually, I think it's called Gateway Lab Room Schedule, guys. It should be in there. I hope it is. Yep, there it is. It's in 11 by 17. This is the document. If you don't have a document, okay, all right. Yeah, this is the document that you have to have. That's what you have to have. If no one showing up without it, this is going to give you the values of this fund. Okay. So you're going to be out there verifying that this system is working properly, and you need to have it. It's just a spreadsheet that we give to you by the designer. You should have a copy, of course, task sources. I would have it in the folder. Basically, those are the folks who should have it. Quick question for those of you who are getting on the field: are you getting these documents? I'm always curious. Because you guys in the field are getting good. Sometimes I get some horror stories.
A lot of times we do on a worksheet, and they're able to say, okay, these are one side that says it's a field verification, run with this.
Yeah, as long as you're getting it, because sometimes I get horror stories. You've got to have it. Now, so it's pretty simple. Here's your room number, right? You go across this way, there's information. Let's say you're in room, I don't know, let's say you're in room 106, okay? Of course, you come down to here, and you end up seeing my cooling minimum is 550, and my cooling max is 1,000, like 1,100, and so the minimum is 550, maximum is 1,100. My heating max is this. My cooling set point is 74 degrees. That's it. Those are the numbers you can really kind of zero in on. Anything else is nice to know. We'll talk about these numbers a little bit. But that's what we're That's really that simple. Design engineers, are you producing these or are you getting them from the task field? What are you getting?
We're designing, we're producing them.
So you guys are putting these numbers together. Oh, okay. Perfect. Wow. So these guys are putting this document together. What's going on? And then we can't do it off of the field place. Exactly how it should go. Anything else on that? So we're going to refer to this in your lab. Okay, cooling on cooling supplement? Oh, yeah. Let me pull that over. It might have got stripped off. Yeah, it should be occupied heating set point, occupied cooling set point. Because you can have both, of course. And then the control that distance is going to be used when you get into call for beats. We'll talk about that a little bit. You can have a different, notice here, you have a cooling min flow, you have a heating min flow. You can adjust those depending on what's needed. You might be going, hey, I have 74 degrees for cooling, 72 for heating. And if we go below 72, my minimum is going to drop down to 100. You can do that. Well, the box will do it. It's not a big issue. It's just a matter of programming. That means the damper can pinch down more because remember, we've got 55-degree air going in. That's pretty standard all year round for a VAV system. 55-degree air. So you're saying, hey, we're going into the heating cycle and it's going to call for heating. I'm going to pinch down more on the damper. You can do that, sure. That would have to be right here set up. And then the task person or the controls guy would just override these things. So you verify that as well. Anything else? No. You're going to definitely use this when you get into the lab. All right. All right. Now, the scenario goes like this. So you're at a job site, you're at a site, and you're thinking, you know, let's use the head end to do this verification. You know, you get the sneaker wear in, let's just go up to the head end, we'll verify every room, and then we get out of here. Keeping in mind it hasn't been signed off yet. So you don't want to go off with the room. Okay. Here's the story. So what is this? This is a commissioning tool, verification tool for jobs controls in this case. Every vendor's going to have their version of this. All it is a window into that controller right there. I'm just looking at all the numbers plugging each other on. That's all I'm doing. So I've got my laptop connected up, going around, and I'm looking into that thing right now. What's important here is this. The process variable. That's the calculated CFN. Remember I talked about this number here? That's the number that's coming out of that calculation. That's the number that's back to the head end. So when they take this point, we map it back to the head end. You're looking at it. And, oh, okay. So it's 250. Oh, look at this, 250. Let's go. Let's sign off on the room. Need a volunteer? And we're going to take a measure. With this thing here, all you do is just do the IO button. And you don't have to push the read button. Let's go right up to here. And all you got. Yeah, so who the hook? Not so here, did he go? He doesn't come up right there it goes. Which is saying they have I think this gentleman said the flow hood says 80. The controller says no, it's 250. Now, obviously, the flow hood's right? We know that. That means there's a problem. In other words, this number's not right. Because my money's on the flow hood, right? Assuming it's calibrated and all that. So we know that's why you wouldn't be doing this at a head end. You signed off on this room. This room would really be started. Really started. You get the idea why you don't verify at a head end. Once you've signed that room off, sure, we're good to go. It's a head end. You're looking at all these different things. But until you do the actual verification, you gotta make sure it's right. You get the idea of the So we know there's an issue with that little controller right now. We're going to find out what that problem is. Get the idea. So we know we're not getting the right CFM. Any questions so far? Okay. So the calculation that's being done by the controller. Now I'm going to go a lot deeper. Now we're getting into calibrating the sensor, which is something you typically would not do, but the core is asking to give it how they adjust keep your eye on the prize. This. That's the takeaway. Now we're going to go deeper. If there was a problem, what would someone like me be doing? We're going to get into that right now. So far, so good. So, so you know from your discussion that CFM is what? A function of velocity, feet per minute, times area square feet per minute. Right? Feet, square feet, cubic feet. Okay. So feet per minute is simply 4,005. So feet per minute is 4,005, and airflow constant at sea level. Yes, it does change as you get into different elevations. But we'll assume we're down here at sea level, 4,005. Square root of velocity pressure, that came from right over here. Right? You work that math out times area. Area is always in square feet, and you're good to go. Right? So that's what's going on. This is what's going on inside this, with one little change, but we'll talk about that. So this is velocity, like sticking your hand out of your car, right? That's velocity. You put an area around your arm, now you got to think. So think of it that way. So here's what's going on. There is one little caveat, that is right here. A multiplier. Right there. This is where things get a little dicey. Okay, what's that all about? Let's go back to these flow rings. Okay. The people who make these boxes design this flow ring understand that when you're at minimum flow, that velocity pressure you're looking at is really, really 0.01. And that's, we're talking about accuracy. For essentially, it's got to be cheap. We don't have an electronic circuit. So they got to get around that. They boost that signal up by actually multiplying it. And the difference is, and it's done by the hole, it's not the machine. So what happens here is they'll boost that up by a certain number. And the trouble is, every manufacturer who makes these flow rates has their own number. So there's no industry standard. You can't say, well, every 8-inch box has a multiplier of, not as work that way. So you have to have that number for the manufacturer. You're going to do a lab, you're going to calculate it. Just that. And that's how this goes. There's also another factor to consider. When you look at the flow profile, your total pressure, it's pushing against what? The static pressure. It's actually putting a slight drag on the static pressure, which means you're not getting a real accurate velocity pressure. So to correct it, that's how they get into the multiplier. And that's basically, it's also called a pickup game. Sometimes it's called a K factor. It's just the way it is. But it's something that the vendor puts together. It might be 4.2, it might be 1.9, and all that stuff. I mean, you can get it, go online, go to the vendor and get this number. But I'm just trying to illustrate that it has to be accurate. So what they multiply here, what do they got to do here? Divide it out. Makes sense, right? Math-wise. So you've got to enter this number correctly, or you won't get the right output. Also, you got to get the right area. So there's two things you have to do. You'll be doing that in your lab. Any questions so far on that? That's too easy. Fan-powered boxes, let's talk about that. Fan assist fan powered. Two types. they're very self-explanatory. The series fan, which means just this, you've got your the airflow from the air handler, right in series with it, there's another little fan, usually a fraction of horsepower, 20, right in series. It's a boosting pump, is all it is. It doesn't get varied, it's set by the balance of the stuff. What it is. So you've got that in series with the main flow. What happens here is that fan will come on when this box controller is told to go on. So there's no software block. It gets it through communication. It's a global variable which comes down to that bus. Okay. It does come from the head end, so the head end will have the time clock, if you want to call it that. Which is, hey, it's 6:30 in the morning, time to start up. Alarm. So what will happen is the damper will do what? It will go to minimum. And if you have a series fan, it goes on. It stays on all day. It's on cycle. The only time it goes off is what? When it's cold go on. That's pretty much it. So it's real simple. But you got to verify that it did it. So a series fan, pretty simply. Next one is parallel fan, and you guessed it. And you've got the main airflow right next to it. It's going to be a little parallel fan. What it's doing is pulling in plenum air. Okay, right above the ceiling tile. You're trying to get the BTUs that are in this room, pull it in, mix that air with the main airflow. That's it. So you've got a parallel fan right next to it. And it's only going to come on call for heat. So to illustrate that one, okay, so max damper, max flow, inflow. As soon as we go below this 72, it's probably going to be a little dead man. But right around here, you have a call for heating, right? Because you're below the set point. Okay? It says, hey, I need to get some more heating. It'll turn that parallel fan on to pull in more plenum air to do what? Bring it back up. That's all it does. So on a call for heating, it goes on. When it gets above the set point, it goes off. Good cycles. That's really the heating. And all you got to do is just have the controls person or task person override the room temperature, which you can do in software, saying, hey, make your room 72 degrees or whatever the winter set point is, and make sure that fan goes on. It's real simple to check out. You want to verify that that fan's going to work. When you get above this, probably a little differential right here, the fan goes off. That's it. Simple as that. During that time, where's the damper? It's at minimum position, which makes sense. You don't want a lot of 55-degree air coming in. So now you're going to have whatever the flow is supposed to be. Remember, you can have a cooling min and a heating min. So the cooling min may be 300, but the heating min might be 100. At that point, this camp will go to 100, each now even more, and start to call for heat on that again. I get the idea. Okay, a little more on this one. So it cycles all day long. Here's an interesting one. You could have reheats. So yeah, if you're I used to live in Wisconsin or northern Minnesota or whatever, it's cold outside. So imagine, if you will, that you're looking down on the core of a building right through the roof line. You can have interior zones and, of course, exterior, and, of course, outside air, right? Surrounding the building. Makes sense? Let's just say right now it's a balmy minus 20. Okay? They might have this. You might have base 40. you got a good chance you have like glass, you know, that kind of stuff on the exterior zones. So what they might say is, hey, we got the parallel fan on right about here. We're going to call for our baseboard. So what we're going to do is begin to, as you get colder and colder, begin to do what? Open up these little valves. These are only like, 3 GPM, 4 GPM, right? That's what you got. But, it could be 180-degree water going through there to do what? Put up a curtain or a wall of heat. That's all you're doing. So the box controller is saying, well, okay, we're not going to make it recline there, so I'm going to start opening up the baseboard. That's what I'm going to do. Permanent or baseboard. Could be electric. In this case, I drew it as a hydronic system. So now we're starting to do what? Trying to do is get that enough BTUs going to pull the room back up. Also, besides providing some heat in the room, what else is this doing? It's also keeping those windows from what? Frosting up. Because when you get to minus 20 out here, the surface of those windows, what do you do to the dew point? You drop it. Well, what's going to happen? Ice. You have ice on those windows. That's another reason, too. So it has to do with purpose and all that. So you've got the baseboard. Now, you could also have the situation that maybe we get down here. You could call for reheat. Now we're talking about a separate heating circuit. So there might be electric reheat like this one has. It could be water hydronic. Again, we're talking slow amount of GPM. We're not looking at a big valve, an inch and a half, whatever, type of valve, 3/4 of an inch. It's sitting here. The box controller then will say, well, okay, I'm going to give you everything I got in the baseboard, and I'm going to give you more on the reheat to do what? Pull everything back up. So it's that simple on that one. You don't have to have both. You can have just reheats. You can have just baseboard. As to the controller, it doesn't make any difference. I'll program them any way you want. So it's a matter of what you want to have. I can have reheats first, followed by baseboard. It doesn't really matter to me as the tabs controls guy. It doesn't matter what customer want. What do you guys want? Are you guys doing auto reheats? That's your design guys.
I know our reheat stuff most of that reheat.
Hot water. How about the rest of you guys, hot water and stuff like that? So I wouldn't know. Okay, I wouldn't should be back to that aspect. Okay. Yeah, so anyway, that's what you've got going. The interior zone is typically cooling only, which means we have a box like this, small little box, it's going to be a cooling only box. Mainly because you're surrounding this, not with minus 20, you're surrounding it with whatever, 72 degrees. So you're not going to lose, there's not a big delta T from here to here. So that's usually not going to be an issue. It depends if they have to. That's typically because we're cooling only box. That's what we're showing here. There's a series fan. So here we got the controller. We've got the fan right here. Series, just like it says. There's our reheat right here. You may or may not have that. These don't have their reheat. But they're not showing what any
On your picture that you just there, you showed the reheat like that, all the down line.
Yeah, that's a
With the
that's a good question. That's a good question. When I showed drawings here, this is not an install drawing. This is an install. Yeah, the question is well taken. So it looks like, whoa. When you look at a control flow drawing that someone like me created, I don't intend this to give you distance. It's just who's first, who's second, who's third. Oh, okay. No, that's a good question. If this was a mechanical drawing, that's a different story. And I got to show, so the machine metal guys, all the plumbers know what to do out there. You bet. That's a different story. That's a different drawing. As a matter of fact, I would take their drawing, strip it all down to this, is what I do. So I present you with a control flow. You guys are probably not natural mechanicals, I would assume, right? Help me out. I'm not sure. Okay, I'm just sort of curious.
Well, I haven't done it enough to know exactly what we would do.
Okay. How about the rest of you guys who are doing design and stuff? You're probably getting more involved in the actual install. I want this here, I want this here, 5 inches, I want that, whatever. I got a screener on my hot water, my line, and I want it here. That's a different story. But no, it's good point. This is not. This is a good catch. This is just electric. That's what this one is. If you look at the other, you actually put down, and you've got, so many BTUs per watt and all that kind of stuff. For the guys who are like out in the field, this becomes a critical number. Meaning that if you have electric reheats, there's going to be safeties in here that says I have to have a minimum flow for stage 1. I'm not going to turn on my first stage until I have a certain amount of flow. So I have to see, in this case, 70 CFM for each kilowatt. So they have to have that, and that's just a matter of field adjustment. Because what happens is you don't get enough flow, the first stage will turn on. And I've seen that happen more than once in the field, where they didn't get enough flow across the safeties. That's not a function of the SO controller, it's a function of the box itself. And yeah, of course, if you're going to work on these things, you're high voltage, so 277 on up because you're powering the electric. So I know our techs used to hate it because they got to get PPE here. So we're up on a sit ladder, mask, leather gloves for the laptop. They're not going to have to, but they got to do it. That's the way it is. So that's basically it for the electric heating side. This kind of does a recap. So this is something that if you want, you can take a page like this out to a job site and go through it line by line. So starting with, are the diffusers set up in the box? If you get any questions about that, here's a big one. Does it maximum CFM? The final CFM? Final CFM would be what? From your link station, just like we talked about. Minimum CFM, straight seconds for heating. You just go through this punch list right here, and you're going right down this thing. If it's independent, does it have at least one required single static? Have you recorded them? Have you been recorded? So, just a nice little performance. Function performance is a good setup. Sure it is. I mean, just kind of read it down. So the hit was a secret world spot. Okay, what we're going to do is get the last spot. And long guy. We're breaking into two groups. You got a group here, you got a group here. So let's start out with right here. The idea is that all the VAV boxes are going to do it along this corridor, starting with room 101. Each diffuser is marked the room, so you know what room you're looking at. So you have to go all the way down to room 101. What would you ask about this? Using the flow hood. This happens. You're going to record the readings, and you can get the zone temperature by the arm of the flow hood. Put them all in there and get them up. The same group. Sorry. Well, what you do is bottom of page 10 is another table. I want you to fill this out. So you're going to go to each VAV box. You're going to fill in the dual duct, you got any fans, any reheats, things like that. Is it DVC control? Is it directly control? Pressure dependent or dependent. You go to each box and fill that out. So these folks are going to be walking around here. The floor light's right over there. Now this one here, on this page, you're going to need your room schedule. We took a look at earlier, right? And you're just going to fill in your schedule. You don't have to go to these boxes. But the information you're looking for here is on that room schedule. I want you to fill that out. And also, if you've got electric reheat, things like that, and fill that out with your So you're gonna need your room schedule for that.
They've got that for you. Environmental is not that.
Um,
They got more than one, and they, somebody donated that. You go outside, there's a cooling tower out there with the chiller system. The chiller was bought, somebody replaced the chiller.
you don't have to do this step right here, step 2. So you can
They
take
can
that
buy
out.
out, they just turned it in, then I have to make it work, but if they get it on cooler, that lab on
Page 11.
So they have
Number 2, and
power
it's,
with,
you know, across this out.
so much stuff in there. It's like all kind of hot cars.
But you will do the next one.
Look at that much. They also have, see all the VAV boxes. They have all of the VAV. People out of Texas. Followed up and wanted to know if they paid for shipping. They have all
We're
the
gonna start
VAV boxes.
This page, you're gonna start on step 3.
All they had to do was pay for shipping. Everything I had was they brought them in. And
What you're doing here is this. You're gonna be adjusting
what the parameters are. It's not a mechanical box, but it's
such that when you're done,
a lot of good support.
when you're done with this whole section, the flow hood
Okay.
that you measure here, the value will equal the calculated value. So this station here is going to be working with. You're going to be adjusting these two numbers right here, such that when you're done, that value equals the flow rate. That's the main thing. Your correction is right here. Your differential pressure, as measured by that, right there, those two hoses, it's going to be seen right here. Actually, Y delta T. You need to get all these numbers. You're going to calculate a new pickup gain, or a new multiplier. So you're going to be dealing with this diffuser, that little box controller, and the inlet diameter of that thing is 6 inches. So you're going to need to calculate the area. Now you can get it in a couple places. You can go back all the way back to oh, I know where it is. Hold on. On page 4. On page 4, you make a note. This gives you the diameter. That's your square foot area. Remember, you're going to have a round piece of ductwork, right? Or flex duct. You got to project the square feet. So this little cheat sheet just says, if I have a 10-inch diameter, my square foot area is 0.545, or you can round pi up to 3.14. Pi r squared divided by 144. There's 144 square inches in each square foot. That's what you're looking for, is square feet. Right? So when you're in the lab, you can either use this method, or when you get into the lab, you can use this. So, what we're going to do now is you're going to start out with about a 6-inch inlet. You're going to write that down. Now you're going to enter it in the software. Okay, so when you're in lab, you're going to actually change this value. Double click on it. It's simple. Whatever you calculated, put it right in here. That's your first step. The correction to override. Wait about a minute or two because you really upset the PI loop inside this thing. So you got to give it a chance to settle out. You can't try to spill correct efficiently. I want to give it a little bit of time. So you got that value, put that there. Wait a few minutes, then you gotta wait. You're not taking the flow hood. And you're gonna go to that diffuser and measure the flow. That's what you're gonna do. You're gonna write that down. Almost ready. From there, what other value you're gonna get is the differential pressure. You're gonna get the differential pressure right there. whatever it is, you write that down. Okay? And you're almost there. Calculate a new pickup gain. Go back here. Okay? And you're going to enter that right there. Whatever you calculated here, you now enter here. Wait about a minute or two, let the system settle out. We're going to take another reading. This number should be within 5% of the flow rate. Okay, so one group, you're going to be walking, I don't know how to do it, but you're going to flip flop. So one group's going to walk up and down this corridor, the other folks are going to be working with my laptop. So, I'll let you guys go. I just want to do one thing. Hold on, guys. Go ahead with you. Okay, we got it going here. All right, so the group is going to work here. Bring your calculator from your phone. They can use mine. And here's what we're going to do. So I'll let you guys keep going. Let me move this out of the way.
Okay. Hold up. We got to set the black plug for it. Couldn't take this one out. I think what we're waiting for is the bit to set. that's in that area. Yeah. Yeah, pretty close to that. Yeah.
Now, perfect. Yeah. All right, guys. All right, do this little laps. I'll change these numbers. I want to give the other guys their answers. Good job. Good, good. The numbers look great. Good.
Let's see if we can we can go ahead and identify them. Yeah.
Oh, I didn't mind. Oh, it doesn't matter. That's, back to the back here. Okay, so that's back down to our goal. That's the one on it. Where does the other one go? Question for you. Question for you. Now, notice through the mechanic here. Let it go over here. Let it drive over here. When it's independent, pressure. See what one, but up and come over and come back. Look right there. Where does the other one come over here?
Well, actually, that comes from that comes from the pneumatic controller. So this is still
So it comes off the main line?
right. So this is a pneumatic controller that takes those different pressure and controls the pneumatic right because of that actuator right here. So this
Okay, so then I'd be looking for another piece of the box.
right. It's a pneumatic.
Oh. Okay.
I get calculation. Yeah.
So we do the good reading.
Before we get to the girl here.
Hey, I bet you this right here does one switch, different back to two, 8, 9. I can get one button.
If you have your unit early for
We better go back and check it. Is it a big weather heating over the span? Hope the numbers down.
yeah.
From 83, 66, every time it's long. Yeah, that's why.
So I was doing that first one that played it is can't take it to life. So you have to play, you got the system. That one you manage, but when you get that play, because it sounded too bad. $255, $650, $83, Yeah.
All right, you other guys here, the station is open.
When y'all at goes up,
When you're doing that last lap, you'll be working with this screen right here. And you're going to be changing, again, these two numbers. And remember, the end result is whatever you see here, you want that to equal your slope. Changing your area. And this one is apply don't compete right there. So I'll let you guys, you want one or two. Oh, yeah, not clear. Okay, you skip that part. There we go. Right from there. Like this one. You start right down to step 3. And you get all down and do all of this. Oh, yeah, no, 102. Right here. You're already in the right place. That's
there you know, folks. It wasn't reset. It's already set. 179.
Well, wait. That's what it's calculating. We don't know if that's right. So you're going to follow the lab right here. First step is right here, step 3. You're going to change the area. What is that area in square feet? We got a 6-inch inlet. There you go. So, good point. Now, double click on that.
So the area.
Yep, area. Now put in your numbers. And do override. Yep. The override. Now wait a few seconds here. Then you got to take
Now
out.
it's got to catch that.
Let's go for everything.
Now enter the value of the big ass. Using the flow rate measure and note the seal temperature.
But you want to wait a little bit here, let it settle out. And then you got to fight for the flow into these guys.
Well, no, we'll just let them read.
So now what you're going to do, actually, is sit on our table. You go ahead and measure this computer. And you're going to write that down. So you can guys get going, that little bit right there, just conceal it from under nature, the flow right out of there.
We'll just see what
Are they just,
are they just
Yeah.
starting, they already do that?
yeah, the sitting gravity, you only need it for a few seconds.
Look, it's changed?
Yeah,
Because you changed that number there?
yeah, I changed that area.
To 106 inch, we're working on the control part now.
Yeah. Okay, want to steal that left for a second? Then just take a
Now
read.
go ahead.
Yeah, go ahead.
You like me to read
Well, you can get their reading.
Yes.
Yeah, what the
Yeah.
That's right, it's called partnering.
There you go. There you go. They're smarter, not harder.
Just keep going up. It's like there's more road.
No.
204. 204. Okay, write that down. 204. Now, for you guys, there's the differential pressure, your last start. You put that in. Right there. You see, 0.2 inches. Now, we're focusing on 4,005. So just plug and check some numbers. Roughly, we'll pick up here.
Oh, I bet. And two, y'all want to use two rounds?
Yeah, okay. 1, 2, 1.
2, 1.
So you got cheated?
Yeah, 0.0.
We've got great memories, huh? Good, good. That's good. Well, yeah.
That whole answer, or that you still got to still working on it? Say any more?
So we're,
Yeah, that's it.
yeah. So then it says go to the two-shot thing. And then put that in the value. They do
That's what I said.
425, 63. Yeah.
with that reset this one. So that will go back in. Yeah.
There's a reason. So that's what it is. That's the same thing. Yeah, hold on a second, guys. Is it time? I got you right here. Got a high number, that number is right.
Who?
They were way down.
It's,
Now, did you square it? Take that number. Well,
Yeah,
take the
if you're
area.
baseline.
Oh,
That's
okay.
it. Right there by this,
See,
if you get the square.
I could barely see light. I was all fuzzy. Like, what is that? All of a sudden, my wife's face is just like, I think our pocket dial. You called me, so definitely. Everybody around you is like, I saw it earlier. Been 3.5 hours, so I'm guessing I'll get my first half.
Yeah, here it is. Or on the double B. Yeah, whatever.
Are we supposed to have the last pick? I don't know. We didn't. I'll figure out the circle. I didn't think you said it here. I got it. Yeah. I don't think we were supposed to see it just a bit.
What do you mean, BQ? What's that?
Yeah.
So I mean, you're right. This is great. Right. I guess you're over here.
Yeah. I opened my curtain. I've been like reading, watching movies. I gotta get out of here. Open the curtains and kind of see what it's like a vampire.
Yeah.
That was a bad thing.
Did you put your hair back yesterday?
Yeah.
Yeah, I saw you walking around. I wasn't certain it was you though. It wasn't something different.
That was me. Just walking around downtown, feeding just I ate one shift at my pretty good. I got ordered feet the road.
We didn't have that period.
So I come back on the road and took it all the way past our hotel to Tempe. And then I got an ice cream sandwich at the Big Bear. Yeah. That's an ice cream
Yeah, you
sandwich.
still think I'm still thinking.
Just walking
Yeah,
around.
you still.
Make my watch set up walk about 7 miles. It was, I was just blown away at how little traffic.
There you go.
For the size of the city, it looks like most of the time I was just walking across the street, not even paying attention to the walk signs, because there are no cars there. And you know, that was like 10:30 on a Wednesday, 7:40 because business traffic.
I don't think we'll try
You're good.
So you have to have an app on your phone.
Good number.
You take a picture, and you have to put credit card on that, obviously. Take a picture of it, and it'll unlock. It's based on how.
All right, guys, this is kind of going to wrap up.
Done. You just click on the app that you're done.
Want to review a little bit of this?
leave it short.
Oh, yeah.
As long as it's not like a legal part, like you can't just leave it. They have them that say, it is fun. Like sometimes they'll go to the they won't realize how fast they are. And so they'll like the street plates in the road. That's great. People like reading.
All right, let's take a look at this, guys.
All that.
We're on page 10. Let's go back and take a look at this full chart. Do a review. So tell me about room 101. Is it single duct, dual duct? What they got going on there? Single duct. Any fans, any reheats? Nope. Over here. All right. 102. How many five in? Okay. Anything else going on? Nope. How about this side of it? Easy. Okay. Doing 103. Hold up. No fans in the east. How about this side of it? Easy. Yeah. 104. A little different. What's going on with 104? Got a series fan. Otherwise, everything else is the same. Single duct. No reading. And over here you have PEC. 105. Single duct. Any reheats? Nope. Good. For those of you tomorrow who want to take this, I know you got choices for you. You come here tomorrow, we're going to climb all over that. Get it big time. So just give a heads up on that. You can do. Bring this book with you. Oh, that's nice. Thanks. What's that class called? This will be the VAV air handler. Yeah. What do they call it? Air system. It will be air handling in a truck traverse. We're not really going to be doing a traverse. That will be over there. This will be just a VAV air handler. So it would be skip the truck traverse. So it will be VAV air handler. It's labeled air handling unit. Truck traverse is going to be over there. So if you want to do the VAV air handler, that's always come on over here. All right. Any questions?
There's so many like these.
Oh, yeah. All right, guys. Thank you, student notes, and thanks again. We'll see you tomorrow.
This name has killed more people with his nickname than most people ever.
He's the president of the United States.
All right.
The next dose.
You got it, sir. You got it. Did you bring your lunch?
No, I did not.
What you got? How do you want to do? I mean, I brought something, but I can save it for tomorrow.
Well, actually, I didn't bring something, but I had something left over from last week. So I could certainly do something.
All right. Good. Pretty good.
That's a little chilly, isn't it?
Yeah.
What's it do with cameras?
Log in. Make something. Yeah, my wife helps us that. Here, why don't you spend like 18, 30, 30, 30 hours? Every time you go anywhere, rain is under 50. The weather is like 55. You're going to take stuff out of one luggage and put it on here and on something. That's going. That's your body stuff. Doing it's a little stuff.
Oh, there's somewhere before that, you said, we're not up, two on one back, go pull them out, and stuff.
I've been wearing none of them. I've been wearing t-shirts and, the TVs and these are tight here. I brought them on the shirt. Well, I brought shorts. That's bad. I got 3-4 pair of shorts. I got 2 pair of shorts, work out in. And like, I work out one. Monday, I got a white shirt. Like Monday, Monday night football is until 8 o'clock. We don't get back until 12 o'clock.
great here? I know it's great. Let me go one more time zone west.
Oh, yeah.
Yeah. Yeah, I know. It's weird. It's the best place to watch football. It is. Baseball? That's ready? 1, 2 in the morning. Because you would expect that watch it, you know, your mind, you know, yeah. I figure if I would say all this stuff, so if I just do it for myself, guarantee
You got 7 or 8 in your group?
Seven.
You got 7. Okay, we'll get started. Great. All right, guys. Welcome. Let's see. I'm Dave Kenny. Just call me Dave. That's fine. 32 years with Johnson Controls, and I'm retired. I still do some work here teaching. Other than that, I'm just lazy now. Get away with it. The only trouble is now I'm around to do more honeydews. That's the downside. You guys think about retirement? Yeah, it's not over yet. First thing is we've got student notes right here. We're going to be working out of this one today. The way I've got it lined up is today we're going to do VAV boxes. Those of you who will come back tomorrow, if you would like to, we're going to be doing the VAV area. That's how we're going to do it. And then you have to bring the same books. If you want to come back with the VAV area, that's fine. And then we'll use this book as well. So we got that going. A couple of things before we get started. I would like to get to know a little bit about your backgrounds. Your name, of course, your title, but what do you really do day to day, right? What I always laugh about, your title is for HR to tell you, that doesn't mean that's what you do. Your boss tells you what to do, right? So, also, are you in the field more or in the office more? Just trying to get a handle on everything. So,
Rick Wall, we got a Philadelphia district, we're like water, New Jersey. I'm on QA, or on 50/50, in office out on the field. I do work for myself in 25 years as a general contractor before I started stuff. And I think out of all the trades, HVAC was one of the weakest. And so I wanted to, and then now I'm going to QA. Know what you're doing with water.
okay, good. We'll go across right here.
John, I work for New York National Guard in their facilities. Basically manage design digital projects.
Okay. And you're in the office 50/50?
No, pretty much 95 and 5.
Okay, good.
Joel, I work for the Omaha District Corps of Engineers. Most of my time is spent in an office, but I have been on site as a project engineer.
Okay. Back here with
John, QA/electrician. Most of my time is spent out in the field. We got a big project coming up. We're going to be doing HVAC on VAV.
Okay.
My name is Kevin. I go to plant mechanic. I do all PMs, so 95% of my time is out in the plant. Putting renovation.
Okay.
My name is David Stauer. I'm over this working here in the QA office.
Greg Sykes, originally I was working with this Greg Academy. Currently, work on and budget engineer, about 7 years, 8 time here we are.
A little background. What I'm going to do is, while I'm going through today's presentation and tomorrow, would be a little bit on how the stuff works, but I'm more or less going to really position it so you're at a site doing a tab verification, performance verification. That's how I'm going to treat everything. So the real trick is, what do you need to know because you're at that site? What questions to ask of the contractor? So you might have someone working with you, that's fine too, but that's how I'm going to look at it. So at the beginning, Ask any questions. If I don't have an answer, I will get you one before you leave, or one of you guys will provide it. So we will get you an answer before you leave. So that's really the whole thing. With that in mind, let's get started. This first page is, you probably noticed you got a whole bunch of tabs. So once you go to the second tab called VAV box performance objectives. We'll kind of cover also what it is we're going to be talking about today. Tomorrow we'll get into specific objectives. So with that in mind, specifically right over here, you will be using some software today, dealing with the VAV boxes. And we're going to be setting up how to calibrate certain sensors when they need to be calibrated. We'll be talking about the type of VAV boxes, including only fan assist, baseboard, things of that nature. Fan power boxes, whatever that's going to be. We'll be getting into big time the room schedule. That's a real important piece of documentation. We're going to be going through that. You'll be working with that as well. That's a real important tool. We'll chat about that. That's basically what we're going to be doing today. Tomorrow, again, we'll be climbing all over that area. And some head-end stuff. I'll be getting a little bit of EAS. That'll be tomorrow. For those of you who come back and everything. Let's kind of move on here. I think that should be the next page. Down to page 2. So what we're going to have is a situation like this. The main air handlers right over here entering the VAV box. So that would be so the air is coming in like so. Or if you're looking at this, the main air handler is right there, dropping. There's a drop right here, entering that VAV box right there. So we're looking at the schematic from that perspective. For VAV, 55-degree air all year round is not unusual. So probably it's pushing out 55-degree air. I'm going to say typically 1 inch of static pressure at the inlet of the box. So we'll use those conditions for now to represent what are the conditions that are in this box. Now it goes in, and then of course now you have your damper. There's your damper, and all you do is going to meter in the air, just like a valve. That's all you're going to be doing. Okay. Then in the real room, large room, you're going to have obviously multiple diffusers and flex stuff going on. So you can have 4, 5, 6 things, how many zones are and whatnot. What we won't be doing here is setting these balancing valves, balancing dampers. You'll be doing that over there with Mike. I think it's tomorrow. So we won't be getting into that part of it. But the rest of it we'll be talking about today. So you're basically going to be in a room, verification, and you're going to be working with a task person, maybe a controls guy. I might be there as well, depending on what's required. And he's going to use a flow hood and be taking measurements at those diffusers. That's going to be the really important part of the whole thing. So you got to kind of visualize that. So let's talk about this. VAV boxes. Two fundamental types. One's called pressure dependent, and one's called pressure independent. Okay? They both have this in common. They both will be singled up, just like that. One inlet coming in, singled up. They both can do dual duct, which means you have a hot deck, cold deck comes from the air handler. She might have 90-degree air in one, 55-degree air in the other, and they're blending in at the air handler. Sorry, at the box. They both can address reheats, baseboard. They both have that option. All being done in that case by this little controller right here. This week, I know you got into a little bit. What about dependent and independent? Is there one style better than the other? If so, why? Do you like? Do you like independent? All right.
Consider it what?
So,
I would say independent steer, but consider it better than all.
okay. And we're gonna find out why in just a second. He's right. The choice is gonna always be independent. Let's talk about the dependent box.
Yeah, but yeah, but a lot of times.
All right, so what we've got is along this line here, the x-axis, we have the room temperature as seen by that stack. Standard temperature. In this case, I've chosen 75 degrees as my set point. That will be a matter of your schedule. Then what's going to happen is at 75 degrees and below, I'm going to be at some minimum position in percent. So whatever that's going to be, it's full travel. As the room temperature goes up, we're going to call for the damper to open up. Well, that makes sense. I got 55 degree air coming in. Yeah, it's getting warmer in the room. I want more air to come in. Then, of course, the damper is going to travel from minimum position to maximum position. While you're occupied, can you ever close this damper while you're occupied? No. So you're going to always, while you're occupied, be traveling from minimum to max in percent. Well, what's wrong with that? Let's talk about that. First of all, the time constant, or how fast a zone status changes with regard to time. How long do you think it takes? Say you're a big room where your guys are sitting, right? How long do you think it takes to travel to go 1 degree Fahrenheit? 1 second, 2 seconds, 3 seconds, 1 minute? Yeah. It could take, depending on the load, it could take 5 minutes. Who knows? You've got a big auditorium. So you've got a slow responding temperature. That's not a fault of the sensor. It's just the way room temperature changes, right? So you've got some kind of a lag already built in. Now, the other side of it is this. With a dependent box, here's the deal. Well, actually, any dependent box. So I'm the salesman. I come in saying, I'm going to sell you this box. If you give me 1 inch of static with the damper full open, I guarantee 1,000 CFL out of this box. However, if you don't give me 1 inch of static, I'm taking all that off the tail. I have no idea what's going to be inside this box. So you can see the problem right away. With a dependent box, too, this controller hasn't got any idea how much air is going through. Not a bit. He's only going to move what? The temperature of the room space. That's the way it works. So if suddenly you've got the box wide open, the main air handler has a problem. It goes down to 3/4 of an inch. You're going to have less air going out. The problem is going to be the dependent box is dependent on the main air handler. That's where the term comes from. That's why you're right, you don't want to use it. So how do they get around it? Well, the next trial, independent. With an independent box, you got flow pickups. A flow pickup is nothing more than a repackaged kilo tube. That's all it is. Picking up the differential pressure. Now, looking at it from the side, you can tell it's independent because it's got 2 hoses. That box up there, is that dependent or independent? Goes here, you see it. Yeah, this little box right here?
Yeah.
What is that going to be? Independent or dependent? Yeah, independent. You've got two hoses coming out. So basically, what you see right there is what you see right here. You got a differential pressure coming out this thing. As measured by this load. So let's kind of follow that through for a minute. So now we've got a different pressure. So we've got total pressure coming this way. Remember, static pressure is the pressure that goes out at all angles, right? So now I've got total pressure right here, being the space, and then you've got static pressure on the other hose. Now you got differential pressure. So total pressure equals what? Static pressure plus velocity pressure, right? Well, we got a differential pressure. That means total pressure minus static pressure is velocity pressure. That's what I've got. Total pressure, static pressure, I'm going to measure velocity pressure. Okay, so far so good? Okay. So, what's coming out of here, going into the VAV box controller, is velocity pressure. You can see now, you've got the hoses hooked up right over here to that little controller. This controller is receiving that signal, and it's converting that into velocity pressure. Okay? Then some magic appears. There's going to be a little calculation. We'll talk about that in just a minute. This thing's going to convert that velocity pressure into CF now. We'll see how that works a little bit later. So now, that little digital controller knows how much CFM is going through it. Big difference. The other dependent had no idea. Now it does. Now I can see or measure how much CFM you got. The only thing left now is determine how much CFM do I need. Right? Well, that's where the second part comes in. And once we do that, we have to set the correct. What I'm drawing up here is another little calculation of this box. You don't have to do it, it does it for you. All this stuff's done for you. What happens here is, as the room temperature goes up, it calculates a CFM set point. Not damper position, it calculates a set point based upon room temperature. So as that room temperature goes up, it's going to say, hey, I need more CFM. It comes up with a set point. So let me give you an example. Let's say the minimum CFM required is 300. Just as a number. The maximum CFM is 1,000. That means as we go from here all the way up, we're going to ask for a set point of 300, 400, 500, all the way up to 1,000. So the hotter the room gets, the higher CFM set point I want. Okay? So let's just say for a minute, the room temperature is right here, and it says I need 500 CFMs. That's what the set point has been determined. So now you've got a target. Okay, now I know what my target is. Let's just say for a moment that the actual CFM is 450. So this thing is calculating we got 450 CFM going through the box. Inside the controller, he says, but I want 500. What's he going to do with the damper? Open it or close it? Open it. That's exactly right. All of a sudden, the air handler has a problem. We no longer have 1 inch static at the end. We got 3/4 of an inch. Okay? If that happens, doesn't that go down? Sure. I don't have the static pressure that used to have. So suddenly we got 400 CFM. So now what is the controller going to do? Open it some more. Pressure changes in seconds, not minutes. So in other words, you get rid of that lag. Instantly the controller is going to respond. You're going to start readjusting the damper. So he's independent of pressure fluctuations at the air handler. That's how the turbo goes up. So if you're independent of pressure fluctuations at that air handler, this box controller can respond in seconds. You get the idea. That's why you go over. Makes sense on why that works that way, why the efficiency works better.
Yeah. Yes, sir. The flow sensor in there, isn't it? Just like that video too. Is there a flow sensor in there? It's just checking static and velocity pressure, right?
It is a kilo tube. It's a repackaged kilo tube. Instead of having two hoses coming out, it's just a package. You're right, it's a repackaged kilo tube.
Okay, so it's not giving you. I mean, you have to do it to get flow. No, I mean, it looked like you were saying one sensor picks up getting the flow pressure, and the other gives you the static.
That's correct.
Isn't it? Velocity, one piece of fiber is going to be the velocity pressure, the other one's going to be static.
Well, we're making velocity pressure in this case. So you're right. What happens here is, as the air hits the face of this pickup, this is picking up the high side, the total pressure. Remember, static pressure goes at all angles. It's pushing back this way, and when he got on the low side, this static pressure. So the differential pressure is going to be total pressure minus static pressure. Remember, differential is subtracting. That's going to give you velocity. So what comes out is velocity pressure. Make sense on that? You're right in what you're saying.
I have a different question. It's not from the actual signal. All the programming for this, those come from the factory or those come from the set up each equipment and stuff.
That would be that. No.
You train or whatever, just sit and raw equipment and things from there.
And I would work that stuff like that. You got to have the same numbers. Right. I would. It's possible, to be risky, that you could drop ship it for all the parts to say Middle Industries have that ability. It's not. You're in a factory in Idaho somewhere, and this job is in Florida. Could it be done? Anything could be done. I wouldn't see it. Maybe done on site. The fabrication,
Yeah. So you're talking about any stuff or whatever you have to do. Calculation of pressure and plug it down.
you guys know. That's part of being here today. You're right. What you said, that's what it's like. Yep. That's what I said. So the real deal here is. In your student notes, you have another little tab called Gateway Lab Room Schedule. It's 11 by 17. Take a moment to find that. Okay, I always talk about this kind of stuff. We're going to get a lot deeper. If you're falling asleep, Here's the takeaway. If you're falling asleep, don't forget this. Min CFM, max CFM, oh, and say a set point. Whatever that set point is. Absolutely must verify in the room, not at the head end, in the room. That's the real big thing. So you might be with a commissioning agent, and you're working on a commissioning agent. You might get a commissioning agent. Like I said. Here we go. Oh, yeah. This guy knows he's much more efficient and faster. That's it. Yeah. Independent, I know what the core specifies. So, everyone find this okay? This is absolute. When you go to a job site, you're going to do some verification. You have to have this as part of your schedule. It is part of your documentation. And you're going to go to each room, whatever's been assigned to you. You're going to have a task person verify right there. Do we have the right numbers? So let's say that you're in room 106. Let's just say you're standing in room 106 right now. You come across here. Room 106 says my minimum CFM is 550. Okay, that would be that number right there. My max number for cooling, 1100. That would be on this graph over here. Okay? So your swing, your travel is between 580 and 1100. That's what's going on. Your occupied cooling, set point is 74. Your occupied heating is 72. Now you're ready to go. So then you say, all right, you're standing in a room, the task person has their equivalent, and you say, drive the box all the way over. So they drive the box all the way over the dam. Then they'll go around to each diffuser and add them all up. And they should all equal 1100. If it doesn't, I'm done here. You don't sign off. Because you're not getting the maximum amount of CFM that you want there. Okay. Then they're going to say, okay, if you got it, great, rise it down to the minimum position. So the capsule guy rise it to minimum position. It does the same thing. Hands up his equivalent, reads all his readings, and he should get 550. If you get that and you're at that set point, you're good to go. You're ready to move on. So it's really that simple. Get the idea. But you gotta have the room schedule to tell you what should the numbers be. Because each room could be a different number. Think about this. When you back up, with these numbers, maximum, how did they get those numbers? Some engineer had to calculate what should the CFM be at design. Not spring and fall. The spring and fall is what you're under a lighter load, right? But come summertime, this year it's 110, you're full load. So you better be getting the right amount of CFM, maximum CFM, or you're not going to be cool as discount. That's why it's so important that when you check it out, you might be there in October, you might be there in February. Well, you're not at design. So you still have to verify this stuff. Say, I'm not going to walk into the room and going, hey, you know what? We're getting here. Let's get out of here. No. That might work in the spring or the fall, but it's not going to work in summer. So that's why you, no matter what, you have to make sure you're getting that maximum CFM. Now, the minimum, of course, is your ventilation there. As you know, you can't close off the VAV box while you're occupied. So that's going to be done. So that's your ventilation. So you got to make sure you got that. See how that all fits together. So you go to each room and go right across, and that's the guys who've been out there. How many guys have done verification? Did you get okay? Did you guys get this schedule I hope? How to check out? Yeah. Good question. Was it hard to get this documentation? Okay, good. That's good. I don't always get that. I get guys going, I don't know where to get this. You got to be a champion here. Champion to go out there and find it. Don't bother showing up. So you have one. It's like tomorrow we're going to talk about that air handler. There's going to be some drawings associated with that. You got to have that. I don't bother. Okay, on that, that's the deal as far as the min-max CFM. That would be pharmaceuticals. That's actually all part of this, but you should get a whole bunch of paperwork. Part of it will be your tax report on the characteristics of the coils and the air handler. The drawings of the air handler, sequence of operations. You should get a whole bunch of stuff. Because what happens is, it becomes your cheat sheet, you want to call it, what questions to ask the contractor. That's really, remember what I told you, you're there to ask them, show me this works, right? Well, the only way you're going to do that is if you know what you're looking for. So that's why you need to have this information, so you know what to ask the contractor. That's good. In other words, keep me honest. That's the whole idea. Keep me honest. Make sure you get what you pay for.
That last you have the top one,
Right?
that last and
Oh.
stage, you have a minimum airflow of heating.
Gotcha. Good. Good point. Yes. This is summer, right? Now, when you get into winter, you got 100. Now, let's let you ask that. That's all programmed into this control line. The reason for the 100 is this. Remember, all year round, we get 55-degree air in most cases. 55-degree air. When you have a call for heating, in other words, you're below the heating set point, it would make sense that I want to go to minimum. In fact, I'm going to go less than summer minimum. I'm going down to the winter minimum. So we're going to go from 550 to 100 on my heat. I want less of that 55-degree air coming in. And that way I don't have time to get my reheats working. So you change it in the winter to be 100. We're going to pitch down all the way down to 100. In the summertime, I mean, it's going to be 550. Why? Because it's hotter outside. And I want more than 55-degree air. Is that kind of answering the question okay? That's why you have the two possibilities of having a heating minimum and a cooling minimum. So the heating minimum, you want to pitch that box down as far as you can go. Less than the 55 degrees. That's why you do it. But when you get into cooling mode, then I want the 550. So I allow more air in.
A true minimum facility 100 CFM. But as you get above, it starts climbing up. And when you read, then it's by the way the program is set up,
Well, let's do it this way. Good question. Let's go with that. You draw it another way. this way. 74 is my summer, okay? My min's gonna be right here. However, when I get down here, I'm entering in the heating side. When I get below 72 degrees and below, I'm not gonna start at 550, I'm gonna start at 100. So as we got from here to here, when I get to here, my minimum position is actually gonna drop, which means the damper's gonna come down, inch down. Does that make sense on that?
I think what he's saying is during the cooling season, 550 is not actually, not necessarily a ventilation.
It is the minimum for the cooling.
The cooler is the minimum.
Well, you need some enough fresh air all year round.
Well, yeah, but I just,
550 is your bottom limit, you can't go on that in heat.
yeah, but, okay, in this situation, they're saying, when we're in the cooling season, it will be higher.
He's not necessarily talking about the airflow into the entire, it's just through that in the box. Well, that's the entire.
Oh, yeah.
It's very well fitting.
Yeah, so what we are saying is, yes, on the cooling side of it, our minimum is 5. Then we're gonna go from 550 up to 1100. That's the cooling side. So when I'm 74 degrees and moving this way, I'm going from 550 up to 1100. I am doing that on the cooling side. Where I'm in the heating side, which is stated by 72 degrees, then my minimum is no longer 550. It goes down lower to 100. Then we're going to go from 100 to max to 200. So we're actually looking at something like this. So what happens is as soon as our temperature goes down below this value, we're going to go to a minimum of 100 and travel up to 200. We're only doing the heating. But when the temperature goes back up, these values go away, and now I have these two values. And that just happens to cycle through on your season. So it makes sense to say, we've still got the same 55-degree air. That hasn't changed. That's going to be the air. So we know we've got that as our input. We're just going to change how much we travel on that damper. So it makes sense to say, well, it's winter time. I don't want to hold on to 55-degree air. I want to pitch down as low as I can get away with. Which means I'm going to go down to off to 100. If the box is supposed to come off forward, they're going to go off from 100 to 200. Only one heating side.
But it's going to use the clutch if you're running outside air.
Oh yeah, no, I'm changing. The air handler is still doing what it's doing. Remember what we did? We're not letting the outside air do. This is all, on the air handler. The air handler has got those big dampers over there. They're taking care of the actual how much outside air you have.
So,
Makes sense on that? So yeah, you're definitely still getting, you're getting a lesser chunk of that discharge here.
so then you can figure it out. You just have to see a number of the and like, you have to do each side and your side. So there'll be two. One.
What happens is, either the test and balance person or me, I can be there, and I can actually override the room temperature. With my software, I can fake out the system. Say, okay, right now the room temperature is 74 degrees. I can turn around and change it. Okay, I can override the room temperature to 72 degrees. And you verify it. Yes, sir. And you would, then you would look for these numbers. Absolutely correct. Absolutely correct. Because you don't know when's going to be there, right? So, all right. So it can all be done through software. You have to see. More importantly, did I get the question okay?
Basically, your minimum is, in your case, is 100.
Yeah, for winter. For the cool.
Of the AV box.
Yeah. Right.
AV box. Well, then,
We're not changing the outside air damper. The air is only. He's controlled whatever his position is, 25%. So that was separate.
it's not as calculated, so that you're going to send it from the air machine this year or outside of the air. Like, so you have different spaces.
Right, yeah. Keep in mind, we're not changing the outside air damper.
Well, the bond limit on that area, maximum limit would be only 3% of the mandatory outside air.
it's going to meter in the minimum outside air coming from the air handler, not the damper over here. You got an outside air handler right over there. We're not touching it. He said, you're right. He's got 25% office space, whatever. We're not even touching it. We're just saying how much of the air leaving an air handler is going through the box. That's what I'm thinking. Yeah, good point. Good question. Okay, so that's something you gotta have. Um, all right, now what I want to do is do an illustration. Oh yeah.
Right here.
Right? Yeah, we got one over here too. Oh yeah. Well, you know, it's here. So here's what I want to illustrate here. So I want to go through a scenario. Let's say that, hey, you're not feeling very energetic today. Let's go to the head end. Check out and verify this room. Why we got to walk around this crazy facility and go to each room? We just use the head end. If the room has been checked out and signed off, yeah, but if it has not, no. Why? This window here that you're looking at is my laptop connected to that VAV box controller. So I'm a window, I'm looking inside that little guy right there. I'm actually looking at all the numbers in their chain in real time. Okay? This is, right now, not this variable, it's the calculated CFM I was talking about. Okay? That's what the controller is thinking is being produced going through the box. Okay? Now, this point right here, this number, is the one that's being seen back to the head end. They call it point map. Map back in. So you're sitting in a chair, and you're saying, wow, we're looking for 180, we got 171. Hey, let's sign off on this. After all, it's 171 CFM. That looks pretty good to me. Need a volunteer. Come on up here. When you deal with this guy, just push the IO button, and then let's kind of take a measurement. Let's see what we got here. First up, let's see what we got. He does come up, you push the little red button on the side. Okay, this gentleman says it's 80 CFM. The box controller says no, it's 170. Remember, that's the number you would see at the head end. Well, we all know you're going to go with the hood, right? And all that. So I know that we got a problem. Yeah, we got a problem. It said it's this, but it's really 80. That's why you go to each room and verify. Once everything's been checked out, then you can use the head end. So we now know we have a problem. That's what I wanted to see. That's why you want to be here. Checkouts. We're going to find out now, well, what happened. What went wrong. That's going to be part of your lab study, actually. So, we come back to this side, page 4. Okay. How did this box controller calculate CFM? Well, just so you learn in class. CFM is the velocity of the air, feet per minute, right? Times the area. So you got feet times feet squared, you got cubic feet, right? Feet per minute is just, you're riding down the street in your car and you stick your hand out. That's feet per minute. That's velocity. It's not CFM, that's just velocity of air. Right? If I could put a piece of ductwork around down the car, that would be CFM. Right? Not a speed area. So we know that we got feet per minute times area in square feet. So we can kind of work from here and say, all right, this quantity here is feet per minute. Okay, that's feet per minute. Well, what does that mean? 4005 is an airflow constant at sea level. At sea level, which is basically where we are here. If I was up in Flagstaff, that would change by about 10%. It changes from altitude. But right now, we're going to assume we're at sea level. So the airflow constant is 4005 times the square root of the velocity of pressure. The reason for that is a pitot tube is not really a linear device. To make it linear, they take the square root of it. That's why there's a square root of it in the first place. So we're going to take that velocity pressure, right? Take the square root of it times 4005. That is your feet per minute. That will time. Okay? Well, we want cubic feet per minute. Area's got to be in feet squared, right? Then you can get CFM. The problem is we got round ductwork. We don't have square ductwork, which is more than 99% of the time it's going to be round ductwork. So we got to somehow get feet squared from that. All right, the problem's fixed right here. We got a little cheat sheet. Let's say your diameter at the inlet, right where the flow pickups are. Okay. If that is 10 inches in diameter, that's 0.545 square feet. That's what you really want. You want square feet. Okay. If you like it another way, you can do pi r squared divided by 144. In other words, 3.14 times the radius, not the diameter, times the radius squared, divided by 144, because there's 144 square inches in a square foot. In other words, the end result is you want square feet. So you need to have it, so you divide by 144, it'll give you the same number. Another way of doing it. You have to have that number to be correct. But we know that right now, there's something wrong with that box control. You do know that now. So we've got the area, velocity, pressure. There is one other thing that I haven't quite put together yet. Divided by the multiplier. Oh, okay, what's this all about? Okay, this is also called a pickup gain. It can also be, it can be called an X factor multiplier. It's got a lot of different names, but it's an important number. Each manufacturer who makes these flow pickups has an X multiplier. Let's back up a little bit. Let's go back to my drawing. Total pressure, static pressure, high side, low side. Okay? And we get velocity pressure out. Now you got to think about this. We got velocity pressure, which is a very, very, very small number. Very, very small. Okay. In fact, this is the velocity pressure across those flow pickups. 0.02 of an inch. Are you kidding me? That's almost like blowing up a balloon. I mean, it's so hard to measure that low. The manufacturers of these boxes know that. So what they do is actually multiply, increase the value. They do it by
They do what?
they actually multiply or they increase, they multiply the value of velocity pressure. I think the velocity pressure times a certain multiplier. So whatever it is, they'll multiply it like maybe, I don't know, 3.7, 2.1. 2.1 times the velocity pressure to increase it. So it's more, you get more, you get a better reading, more resolution. So they actually do that. The problem is, each manufacturer has their own pickup unit. They don't have a standard one in the industry. It's not saying, every VAV box that's 10 inches has a multiplier of, that's not how it's done. Each manufacturer has their own. So we have to get it, you can go online to get it, or you can calculate it. That's what you guys are going to do in lab. Okay? You got to get that number right, because whatever you multiply here, they're going to divide, the controller's going to divide it out of there if you want to gauge it right, the effect, once you go to the calculation. So you have to have this number correct. It's really what I'm getting here. There's another thing too, besides being so low in value. Think about this. You got total pressure moving this direction, right? You got static pushing against it. What you're really doing is putting a drag on the static pressure, it's like pushing it back. Because it's harder for the static pressure to get here because total pressure is stronger, right? Than static. You're actually pushing this thing backwards on the thing. So by using the multiplier, it compensates for that as well. And that's why you have a pickup is to compensate for those two. And looking at this calculation, you need both of them to be right, or you're not going to get the right CFM. We just saw that we don't have the right CFM coming out of that box, don't we? Sure, we saw that. Well, that's because,
What was it, 80?
yeah, it was 80. Right now, it's 80 coming out of that diffuser.
Yeah.
But this guy says, no, it's 172.
Okay.
Well, we know that something's wrong. One of those, and what can happen is one or both of these numbers was not correct. It was never put in correctly. And we're going to figure out how to do that in just a second. Follow me on that one? So
Yes.
that's why it's important that we get these numbers right, because you've heard the old adage, garbage in, garbage out. And this is exactly that scenario. You're getting garbage out, you're not getting the right values because you don't have the right inputs. So these two numbers, the multiplier, also called the pickup gain, remember I told you, this number right here. The area, square foot area, this number right here. So one or both of these is off. No. Well, typically it would be square like you see here.
So your diameter is
Yeah, good question. Diameter has to do with right around the I'm sorry, right around the foot. Not here, right here. Right down here. So what is the area of square feet? Right. That's what we're dealing with. So we got to come up with a solution to how to get around this. Okay. So far on the pictures, are you good okay on this one? We're going to come back to this. Now, before we do, I want to finish a few more characteristics of VAV boxes. One of them could be, I got fans in this thing. This one does not. Got your airflow here. You may have what's called a series fan, otherwise known as a booster fan. It's a good name because airflow's coming in, right behind it, the fan. It's usually a fractional horsepower, like 120, not a big fan. But it's enough to boost the amount of CFM coming in, going out. What happens is this. When you go occupied, in other words, this controller is supposed to go to the occupied mode. It turns that thing on. Well, does that mean there's a time clock in here? No. This is told to go occupied. What happens is the head end system, which we haven't talked about yet, is telling you it's time to go out. They have a weekly schedule inside the head end system. And what happens is that wire right there, that's a communication bus. So the head end comes down and says, hey, we're going occupied. Now the controller goes, oh, we're going occupied. I got to turn on my serious thing. That's how he knows that they're going. He doesn't have a clock inside. No.
Did they get work back to that? Thermostat get work back to the office? Thermostat work back to the office? If I headed,
With the thermostat.
that's the problem.
Yeah, no, the thermostat's only going to be wired here.
So we go to that box.
Yeah. Yeah, the staff doesn't go to the head end from here. Now, the head end can read the temperature, of course. You can say, oh, what's the value of the staff? Sure, it's back to wherever the head end is. Yep. So that's what you've got going on. But when you're told you're going occupied, it's not even head end.
So you get a lock processor and some kind of program, it's not all back in the
Well, yeah, you're right. Good point. The controller only knows how to do its job in terms of that piece of equipment. He doesn't know anything globally. He doesn't know this area.
Digging these systems down and lock them to continue to operate.
If the head end breaks down,
This is a very good example of system of better.
you'll
This
control
is
the
a
rest.
top discharge system.
You do not need the head end to control coming off the house. Or control pumps.
When they want to be this in, they're
Control
controlling
is
what
what
you
you
want
want so long as it's got
to
power.
get enough air to operate.
Even if the head end drops out, you won't lose your ability because of this.
But what they've done, I'm looking
But I won't have the spots.
Well,
Yeah.
spot well.
And for example, let's say
Spot well, spot
the
well.
head end system goes down.
When they put in guiding
Keep
them.
count. I'll never know when to go
Here,
here, but that's. The other big working dependent.
and then here, and here. And essentially, what's happening, so they take this, they divide this piece of over into 4 separate pieces of dough.
Right. Yeah.
They,
The office, like usually the building chief or something like that, that's where the head end stuff resides. We're gonna get more of a picture of that tomorrow.
Yeah, basically, have 4 pieces of dough, we'll do the air, so any air that comes in, is that basically leaving. Line of fact like this, not gonna run.
Okay, so we've got the series fan, we're ready to go.
Now, how would, if you
Now-
were a plan review, what would you suggest, or what recommendations you make in order to get away from this? I mean, if you notice that the architect didn't get a mechanical engineer enough to put it in, what would you say that you could do to go and adjust that? Right, see if check to see if you even have enough discharge. If you did that, between here and there, we might have a 2.5 ton tank, which put a 3, where it would work extremely efficient. Instead of this, we still have a lot of loss right here, but not nearly as bad as this. Yes.
What about, so you say,
Okay,
what about all
you can have another type of fan. That would be parallel fan. It's exactly what it is. You have a box here and on the side, you have another small little fan. Again, it's fractional horsepower. What he's doing is he's pulling the front of air. What's happening is that front of air is being brought in, being mixed with the 55-degree air. So it's in parallel, because it's over here. There's your air coming in, here's your parallel fan. All of this in second box. Yeah, it's not a booster fan. Nope. This is something else. It's the same kind of size there, but it's actually on the side right here. It's airflow parallel to the negative unit. That's what they're
The reason why we have this is the mechanical.
So you can see right there, you've got a parallel, you got a fan right here. You got your primary air coming in. Here's your primary air. Here's your parallel fan drawing in front of
Marcus, you're putting these don't.
So it's pulling that air from the ceiling tile. It's got more feet
Or
or
something like that, or sometimes we'll have to have one side together.
However, when does it run?
I
Well, what happens is it cycles on and on all day long.
They called up here, that you guys.
Well, it cycles on a call for heating. So here we are in cooling.
You want to pay for the break.
Oh, here we're heating.
Got them up here. And that's good. box to the other.
Up in here, the fan is off. The parallel fan is off.
Go outside.
As soon as we get over here,
And there's a fire alarm flash.
the fan comes
All
on.
the water went out. There was a
The
fire.
idea is, oh, we're getting cooler in the space. It's starting to get cold in here.
High and-
So what happens to the damper? It goes to a minimum position, right? We talked about that. So the damper begins to pinch down, letting less of that 55-degree air in, and we're gonna turn on that parallel fan to get the heat from above the ceiling tiles. Hopefully that we don't have to get back up into the room.
It's old, it's archaic,
As soon as he gets above around here somewhere,
and you got it for nothing. They do enough.
so we cycle, like I said, all day long, we go only on a call for heat. That's all being done by that little digital unit. That's all part of this program.
But we don't know who for it.
Sense on that one?
Okay, we can get all back.
Here's a schematic, a control flow diagram. Supply air from the air handler, there's your flow pickups, your damper. In this scenario, it's a pressure independent box. But we have a reheat and you got possible baseboard. Let's talk a little about that one. So let's say that we're in northern Minnesota. If you look down to the roof line, the core of the building, they're going to have basically interior zones and exterior zones, right? So we know the exterior zone, you could have minus 20 degrees that day, okay? Wherever we have to be in northern Minnesota. It's cold out. This is your exterior zone. Okay, so now we got baseboard. So here's the deal. So all of a sudden we start getting cold in the zones. So we're right around over here. It starts to drop down maybe a few more degrees right over here. So my dampering now is at minimum. What I'm going to do, I'm going to say, well, okay, the fan comes on, a parallel fan. I'm going to start to do what? Open up these little valves. These are just little 1-inch lines, 2.5, 3/4 inch, 2 or 3 GPM. And that's what's going through these little heat exchangers, or radiators, or baseboard, perimeter heat, whatever you want to call them. So they begin to open up, and they get a cooking of what? Cooking heat right behind the walls. Makes sense, right? Another thing that it does, besides providing some heat, is the fact that if this is all glass, you got minus 20, the surface of that glass is minus 20 degrees. What's the dew point? It's really low. What's going to happen is the air inside that room is going to condense. You don't have this blanket of heat, you're going to have what? Ice on. You can't even look out the window. So it's got the two burners. I lived in Wisconsin for many years. I know this sort of that. But you can't even look out the window. So you've got to have these not only to keep people comfortable, but to provide that blanket of heat. So the controller says, okay, we're right here right now. I'm going to bring the damper all the way down to minimum. We got 100, we talked about, we can say. I'm going to start to crank open these little valves. So what happens is, when you get right here, if for some odd reason we're still not able to pull it up, you can have your reheats, which would be in the form of, in this case, water, hot water. You've got your hot water coming in, going through that heat exchanger. Now you got reheats. Down here we use a lot of electric reheats, but if you're up there, you probably got hot water. So now what's happening is we stage it. So fan is on first, baseboard's on second, reheats are on third. Now the reheats would be out here somewhere in the zone. So we're going to try to maintain 70 degrees all in the exterior zone. Now, you don't have to have baseboard first. You could have reheats followed by baseboard. It's whatever you need. Or you may only have baseboard. You don't have reheats. That doesn't matter. It's all a matter of programming that control.
The baseboard on first and the heat kicks in, that's the positive degrees there alone. That's the control there coming out like this. You have the baseboard coming on, and this total means that if you're blowing 55-degree air, it comes back and guys are definitely.
Well, now think about this. What did we do to our minimum position? It's only putting out 100 CFM now. So you got less than that 55 degree air.
Less than
Yeah, you got less than, that's the whole idea of getting you down. As a matter of fact. You put less of a load on that's what the heating load on the system. If you pull it off that that's why you
thought
put
that some of your outside air.
now remember, separate from that is your air handling. Remember that outside air damper is still functioning completely separate from the air. But during the winter, back up, during the winter, that minimum position on air handler is not going to change. You can't change that one. We're changing this one. So that air handler still could be pushing in, pulling in 25 degrees. I'm sorry, it could be pulling in 25% of your minus 20. Oh yeah. That's why you have reheats. I'm sorry, preheats on the air handler. Bring that up. So that's a function of the air handler, not a function of the box.
He's something to talk about 55-degree air.
Well, yeah, 55 degree air is still entering in, but you're getting less. That makes sense. We're getting less of that 55 degree air. Only doing the
So hopefully, it's so low that the occupants aren't going to feel it.
well, right. I mean, the occupants are going to feel 70 degrees. Hopefully, if this circuit works right, we should be getting at least 70 degrees. They're not going to feel anything different, really. It's just a question of how we get that air heated back up. That's coming from the air.
I was just a recipient of they want to put in a position for the draft. Nailed it.
Well, okay. There's a couple of things on that one. It could be where the diffusers are located,
Oh, yeah, that
which
would be-
is Mike Ziegler's done a better job on that, but where they should be placed. So the dynamite.
I created my own cardboard diffuser.
Oh yeah, it is. That's a real issue. Now you got to get into a whole other mechanical change. Oh yeah, no, that can happen. Also, maybe they're not pushing you 55 degree air, but 50 degree air. All bets are off the table now. If he's pulling in 50 degree air, what happens to colder air is denser. What happens is it weighs more. What does it do? It blocks. They call it shelving. The bricks are shelving. Bad positioning of the damper, I mean, diffusers, you're also experiencing the possibility of the air cold from the front of the air. So you got two issues. So then, okay, and then you got to go back to the air handler. Find out is the reheats of the air handler working. You got reheats back there as well. So that's different. You can't be pushing out 50 degree air from the air handler. No, that's the whole purpose of a reheat. And that's more likely to happen not in winter, but in summer. Think about this. The air handler, if you're in Florida, big humidity load. What's going on there? Well, you got a dehumidifier. We're doing the dehumidifier. I got to go to 48 degrees dew point. Okay, great. So we got a drip fan that's working. You can't discharge 48 degrees out of the air. So why are your reheats after cooling to bring that back up? But somehow either there or both you've got an issue there. So that would be my guess. Good luck.
When you said the radio panels, those are the things with flat ceiling, right?
Let's see, reading.
Baseboard or radiant panel.
Oh yeah, right. That would be.
That's the thing. They
Well-
put in the ceiling by the window.
Yeah, right. Exactly. Yeah, it could be that, or it could just be they're just into radiation. Or it could be a fin tube radiation. Or it could be like.
hot to the steam. So that maybe they just.
Yeah. So it basically comes down to that heat source can come from anywhere.
Yeah.
I mean, he's just telling the actuator open or shut.
The control is just controlling that actuator. That's all it is. You're right. He's metering in whatever heat source you're using. You're right. You're right. So that's what we've got going on here. You can see a picture of it right here. That's just another version. You could have electric. That's what we do a lot of. In fact, that's what we got here. If you look down here, you can see electric strips, electric heat. And then you have so many stages. Each stage might be 1 kW, 2 kW, or whatever it's supposed to be set up. So instead of having hot water, you would just have that. So now the control is staging the current out of this binary outputs. That's all it's doing. A cheat sheet also known as a good review here. If you have this, you know what questions to ask when you get out of the field, out of the contract to show you. So that's a connected diffuser matched to the VAV. Yeah, so you go around, look around, make sure it's set up properly. Does a required maximum CFM right there match the final? In other words, when you go into that zone and the TAPS guy does the summation of all the diffusers, does that equal the design maximum CFM? We talked about that. Same thing with minimum. Okay. If it's a pressure independent box, does it have a minimum required in the static? Well, you have to figure out from the drawings, is it needed? Have the min and max settings been recorded? Yeah. Show me it's been recorded. So down the road, when we're out of warranty, so when he comes back and looks at this, all the correct values are there. Right? That's what you're doing. Constant volume versus static pressure getting from the TAPS report. Did you get the proper static pressure? So this is a nice little sheet to have to ask when you're looking at the functional performance of that box. And you do it for each and every zone.
Is that sheet in here?
Oh yeah, I'm sorry. This is page 9. Sorry about that. Yeah, he's under the tab called functional performance VAV box checklist. And then you should have this sheet. Okay. All right, now we're going to do a couple labs here, and we've got basically 2 groups, one group here, one group here, and we're going to assign you different labs, and then you're going to swap. You're going to get to do all the labs. So we're going to start out with one group, and that group's going to walk up and down this corridor right here. Each diffuser is labeled, room 101, 102, and so on. So you know that if you're looking at 102, you're looking at that box right there. So the first bunch of guys is going to take the flow hood, and you're going to walk up and down here and take measurements and fill in over here. It also will give you room temperature visual. You can go in and just add it up. So that's the one part that you have to do. The same group, walking around, you go to each box, and you're going to fill out this table right here. So room 101, is it a single duct, dual duct? Have any fans, any reeds? Is it pneumatically controlled, visually controlled? Is your pressure independent or dependent? You're going to fill out all of this on that page. So the same group's walking up and down doing that. Then, remember that room schedule you have in your student notebook, you're going to use that and then fill out this. You don't have to go to these boxes. If you're using room schedule, you fill out the kind of box that it is, the K factor, otherwise known as the multiplier. So fill out this data. That will come from the room schedule. You have that in your book. We already called that out. We're going to be doing that. Okay? So right now, scratch out lab number 2. Okay, we're not going to do it. If we get some time, we'll go through it. So we're not going to do this. Okay? However, we are going to do the next one. Now, the guys who are walking down up here are going to be doing their work. The other group will be over here at my laptop. Okay? You're going to be changing that multiplier area of business. And you're going to start on step number 3. On page number 12, step number 3. So you're going to start here. Now, this is how it's going to go. What you want to do is you go through this lab, you're going to get a new pickup game. Otherwise, it's a multiplier. Okay. That means you're going to be changing this area. I'll show you how to do that. The goal is this. You get this number just right. Whatever number you see here will line up with the flow hood on the back of the pizza right there. You're going to work with 1, 2. That's the whole game of the game. You're going to be recalibrating that sensor. So what happens is, if I need to change the area, double click on it, fill it in, and do override. If I want to change the pickup gain, double click, put in a value, click override. So here's the procedure, do it step by step.
So, you see that outside of your name?
That box, that inlet right there, that's a 16-inch inlet. Remember I told you, go back and look at a little chart, and that'll tell you what that is in square feet. Take that number right here, and then change it in the software, just like I showed you. Do it in the software. Wait a few minutes. And then you're going to say, okay, I'm going to take the flow hood up here. I'm going to measure the new CFM. All right? And you are going to hit that value here. So far, so good. You made a change right there. And you got a new CFM. Then what you're going to do is go over here, and then whatever value you see in here, that's your differential pressure. Okay, so now you've got the differential pressure. And you write that down. So the idea is now, all right, the flow coefficient, you might want to write this down, is 4,005. Times the area you put in right here, that number right there. Multiply it, divided by whatever value you got here. Don't forget the square. I have a lot of people forget the square there. Multiply it times the differential pressure that you wrote down here. That's your new pickup gain. Then you got to go back into the software side. You're going to double click on it and enter that value. Wait about 2 minutes. Okay. Then, final step is take your flow hood, measure whatever CFM you see here should be within roughly 5% of that. And when you're done, just go to the other lab, and the guys out here will come over here. Any questions on that? You guys break up any way you want. I'm going to do it. So I'll leave this screen up here and so anyway you guys want to do it? You guys want to do here and then you guys work here, that's up to you guys. You need a calculator. You can use my little cheapie, or you can use your phone, whatever you want to do.
We'll do the controls part. We'll do the.
Okay, you guys want to work over here? That's fine. Everyone's gonna get a chance to do that.
We got 1, 2, 3, 4, 5.
Yeah, starting from room 101, all the way down this side. You got it. Well, hood's right there. So you guys gonna work on this one over here?
Yeah.
Oh, yeah, good, good. Do you have anybody signed up with you tomorrow?
I don't have anybody not signed up.
Oh,
Say
okay.
that, just, yeah, no, basically,
Yeah. Okay.
I'll ask him. Yeah, so
They're good guys. Ask a lot of questions. That's all I want, you know, that's why, the worst case is like this. Well, you're gonna always get some, I'm not gonna lie. Well, right, exactly. I'll just like that's still well, it's okay. That kind of thing. Did I get my nose? Did I turn myself back on some wood correct? And but don't get your nose. Sometimes you get
Yeah.
that's a small order.
Takes it a while, puts it in, you kind of got what you got.
Yeah, well, it's a slight thing different. PSI, it's like fake, it's like fake, it's a fake beer.
Oh, 203, 204.
That's
And
usually like, generally it's like.
you got 204.
And it's all,
You got a situation that my dad. He said to me, you know something? You want to gamble?
those kind of curls, and we were adjusting this when you're here.
Yeah, that's what I don't know what you're talking about. So you're kind of getting you follow my analogy? Yeah. So you are, all the years I developed classes with Johnson. One. How do we end up over here? Well, this guy wanted that, and that guy wanted that. So the worst way to go on the course. And we need to get that one. That is over Oh, it's kind of like when you're setting the table and you're opening the door, and then we're not going to do the final set. No, now we can actually taste the fruit, and that's a different thing. But I need you to set the tone. Otherwise, pressure. When they come out here, they go pick up all the other ones that doesn't work. Now I know you know. Well, that's all I get us to use more of the guarantee. But check me on that. And even this is still I don't. 30-some odd years. I still something like okay. Oh yeah. And soccer. It's just like your home. Just when you make you go in, so you're over. Oh, yeah. Well, that's what makes it fun. Otherwise, it's boring. Yeah, but I don't know. Professional? All right. Well, if we're out of act like them. How dangerous can we get from one here?
So, I'll let you guys do it. Click on pickup.
How much a word around?
Now wait about 2 minutes. Then you're going to need to flow this and make sure that it's CFM.
And then you realize you're working on the next contract and you go.
Well,
With 2 weeks of change.
Let's say, guys, you're actually ready to take. I'm looking at the change. I think you're ready to go. Take the next one. When you use your fluid.
Were we gonna go to the first one?
No, the 102. You might have to push the red button on your side. Reset them. What are you getting?
180?
Well, what does she think it is? Over there. Now, okay, 180. Look at your computer screen.
The computer screen says 180.
Therefore, you are right here. You're at
78.
5%. Good job, guys. Why don't you do the other laps? I'm going to get it started. Okay, I don't want to give your answers to the next group. That's so good. Good job.
We accidentally had a little fun.
Well, I hope so.
While they were doing measuring this one here, we said.
Well, we can grab this and we can do it right here.
Okay, when you guys are done, that station,
That was the second verse. Now we
Yeah, 337 and 68. We've already read How do you do this?
red button.
the red button on the side. Make sure it's snug. Push forward.
This one, you measured on this one?
We had this.
Oh, you did it? You did it? Okay.
All right, guys, there's a station open over here at the adjustments. If you want to do that one. In about 10 minutes, we'll wrap up.
Air, it's engine 0.196.
It's 24 right now.
You look at 304, you said? Oh, oh. Yeah, that's it. What's that? Wasn't it? Oh, it's called the. Let's see here. What's that? Is that for say 0.21 would probably be close on this. Point 0.21.
Yeah, 3.1. Maybe our that 204 that they measured earlier.
Yeah.
349.
This is reset. Remember?
Yeah, the pickup gain's supposed to be at 3.1.
Oh, that's what we're talking about, wasn't it? Or what do you say?
No, that's the block. Two-stage electric heater, 2.5 kilowatts.
Well, did it have anything to do with the fact that they were messing with our flow? I mean, seriously. When we were measuring the flow on hood 2, it happened to be right when they were doing the.
Oh, don't use your numbers, no, use the number you got now.
So
Well, that's what I'm
on the
saying.
computer, we need to put the 3.1 in.
Yeah, that is,
3.5.
no, yep. 3.1.
So we got to change those two right now, right?
Yeah, so you're gonna use, 3.1 right there. For your pickup, is that what you calculated? Yeah. Put that in there, override it now.
Then go to the area and put.
Well, the area is right, you got the
You
area
gotta
right.
put that in.
You got that right. So now, wait a second here, you got 3.1. Let it settle out,
It's all right.
and just give them a little longer here. Your numbers look great. Okay, go ahead and take a reading now. Make sure you're nice and snug. Push the red button on the side.
Well,
Okay.
yeah.
Lift it up in a second.
177.
And he thinks it's 176. You're right on. Okay, you can bring down the flow hood. So you read 177.
The flow hood reading close to the process variable value.
And
Yes.
Guess what? You're right on the money. He said, oh, I'm 176. That's within 5%.
You got anything? So the
You
cooling
got it
maximum
nailed,
set point.
You got it nailed.
Is it close to the cooling maximum set point? Did you
About 5 more minutes.
figure that right?
Sit tight, guys. In about 5 minutes, we'll be right here.
Point one. That's the area. Yeah, 0.196.
And the pickup in. What'd you put in? There's one on.
Here's one over here.
So, what did I say that?
What
is that?
we put in 204. 204 was, oh, you're doing it back again? We measured 204.
That's what you calculate.
Right? We put in 204. Because we measured 204. So,
Find out the key. Oh, yeah. I never said that.
well, so it's not close, right?
Go fascinating.
Should we check the flow already? We kind of were getting two different points of data based on the fact that they were tweaking it when we first did our measurement. And then, if we did a recalculation with that, we would get closer.
Yeah. Well, the other thing you got to go back is this software and this. Yeah, all right, now we got to do the game. We're not playing it.
Well, we're close enough.
Yeah.
Did you do a
All right,
recap?
guys, let's go over this little puppy.
Alright.
We'll get you guys going here. And before I forget,
Are we on YouTube right now?
yeah, I got a YouTube channel. I didn't tell you guys, did I? And my Facebook page and Twitter. It's all, you guys are all on the net now. You're all going viral. All right, let's go over just this one table in particular. All right. Tell me about the one-on-one. Single duct, dual duct. What do you got?
Single duct.
Single duct, intermediates.
Single pneumatic suspension.
And independent. How about the 102? What do we know about it?
Single.
Single. Did you see it?
The 103?
Single.
Single duct. Vision with vector digital control and independent. 104. What's different about 104?
It has an electric reheater and a series
No, it doesn't have a reheat, but it does have a series fan.
series
There's
fan.
no reheat, but there's a series fan in there. Absolutely. Everything else is the same. So you don't have any reheat at 104. You have just a series fan. How about 105? Yes, great. Great, guys. Go ahead. Oh, yes, sir.
There are 4 hoses coming out of the box. Does that signify anything? There are 4 hoses coming out of the box.
Oh, they were used, they parallel those, the magnet healing on that, right here. That's just the line. It's a piggyback. All it is just, those 4 hoses are here. 2 of them go to a little magnet healing.
Oh, okay.
And that's just for because they're students. Because a lot of the students here don't have laptops. So they have their differential pressure right off the So tomorrow, guys, if you want to come here, this is the VAV air handler. That's what we'll be doing tomorrow. And thanks. And take a break and take off you next time. All right, guys.
Thank you. Which class?
That would be tomorrow. That would be this one right here. I'm getting you want to go.
Okay.
That's when you want to go.
Yeah.
Yeah. Bring your book. Oh, pleasure. Pleasure. Yeah, bring your books too, guys. The ones you had today. Sure, sure.
What's that? You worried about the fly?
Yeah, that too.
Where's home?
What about you?
Omaha. That's not much better there.
I heard that was one of the best cities in the
Where everything looks better.
Is that right?
I would probably agree. Lots of business too.
That Brian was way down.
Texas.
Good.
How many guys are in your group?
They get you somewhere.
8. You got 8? Okay, we'll give them another couple minutes.
We don't get that crappy weather very often, but they're forecasting for Sunday, Monday in North Carolina.
Oh, yeah. You guys equipped for snow? Yeah.
They got no cloud, minimal. They throw that brine. They spray the roads. You know when you're expecting to have their weather because you got all those trails where they sprayed the overpasses, main roads.
It does make a difference, though, I think. As opposed to not doing it.
Yeah, but then everything shuts down. And for
Oh,
2
yeah,
events,
right.
snow.
All right, guys, let's get started. Welcome, I'm Dave Kenny. Just call me Dave. And I had 32 years with Johnson Controls, and I'm retired now. I do some adjunct teaching here at the college and whatnot. Otherwise, I'm lazy. I'm retired. The young guys, you think about retirement, all that means is you got more honeydew time. Because you can't say, well, I got to be at work here. I'll see you later. Get back there.
Go to work and get some rest.
And that's it. So, no rest of the way today. Today, this afternoon, we're going to talk about VAV boxes, right? For those of you who are coming back tomorrow, we're going to climb around that air hammer over there. We'll be getting into all kinds of software and all kinds of drawings and stuff like that. So that'll be the variable air volume air handling unit if you're interested. I don't know if we're signed up for what yet. That's what we'll be doing. But today, we're talking about the boxes. Before we get started, I like to always go around the room real quick. Give me your name, your title, and what do you really do each day, right? Because your title is how HR pays you. That's not what your boss does with you, right? We all know that's the truth. So tell me, and also, are you in the field a lot, 50-50 with the office, just so I get an idea? We'll start with you. Okay.
So I will usually work with the government of Japan and also coordinate the
Have you earned under the field office, the special field office? Chemical QA work, that also engineer applications.
For a lot of guys. Yeah, good.
Gary Erickson, Wilmington District, North Carolina, field QA. That's everything from concrete to civil work.
So you're in the field a lot.
Do similar reviews on
Good.
John Matt, I'm a chief engineer with the Huntington District. I'm pretty much just an end user. We're 100% in the field. We work on service barges on the Ohio River, up and down the Ohio River. I'm in charge of all the mechanical operations.
So you're in the field a lot, like you said, all the time. Good.
Danny Huggleworth, mechanical engineer, 50-50 field, QA, contract admin.
Brian Dalton, kind of these. I do a lot of this
Okay. Good. Nice fix. That's what we're going to do is, the reason why I'll bring it up too is the way I'm going to present things is, yeah, how does some of this stuff work? That's true. So I'm going to treat this as if you're there to do a verification. You've got a task person, maybe a controls guy out there, and you're out there to verify that this stuff works the way it's supposed to be. That's really how I'll treat it. So you might have some of the commissioning agent working with you, and you're standing there. The real takeaway from all this, in fact, all of this, is what questions do I ask? I'm going to ask. We're standing in front of 5 pumps. What do I ask? Right? So you need to know that. Or I'm in front of I'm in a zone like, I want to check out a VAV box. Well, how do I know what to do? That's the kind of stuff. So that's kind of where we're going to take all of this discussions. I got some student notes right over here. And we'll be working out of this. Yeah. For those of you who come back tomorrow, bring this book with you. It's got information on the VAV box. It's also got the information for that VAV airport. So make sure you bring that with you for those of you who come back tomorrow. When you open this up, you can notice there's lots of tabs. So why don't you do that? And go over to the tab called VAV Box Student Performance. So find that little tab and open that up. And so go ahead and do that. And you should see this page, which is page 1. Yeah, we're looking at a lot of that of these tabs. So we can look at this stuff. Okay, looks like all you guys got it. Just want to go over briefly what it is we're going to be talking about, the objectives, what are we going to be doing today, and particularly in the bottom here. You will be using the computer software today and tomorrow. There'll be some computer software stuff you're going to be dealing with. So we will be using the computer software, using the flow hood. Definitely be doing a lot of that today. In configuring a VAV box controller. Okay, we'll be talking about the different types of boxes: dependent box, independent, series fans, reheats. We'll be talking about that as well. Big time on this one, room schedule. That's a really important document. We'll definitely be working out that as well as part of your experience. So it's pretty much everything you need to know to get into the verification of a VAV box. So the next page is page 2, and think of this little graphic right here. So what we're going to be talking about is, this is the air coming from the main air handler, which we'll talk about this tomorrow. As far as this lab goes, if you look right here, this is an inlet. So where I have my finger pointing is right there. In terms of the visual schematic, that's what it really looks like. So I got air coming in, going through the box, and coming out of the diffuser. Now, in the real world, you probably would have more than one diffuser. The reason why we only have one is we're in a box. You don't have space. You can't build walls. But anyway, we got a diffuser. In the real world, you would have many diffusers, depending on the size and space. So the air is entering in, right through here, going through the damper. Then you got your flex duct taking you out into the different diffusers. What we won't be doing here is balancing these legs. We'll be doing that with Mike. If you haven't already, you will do that tomorrow. Kind of thing. We're going to be talking about right over here. Now, so in other words, right here is the inlet to the box. On this box, that means right here. Typical air handler VAV is 55-degree air all year round. They're pushing out 55-degree air from the main air handler, coming down right through there. And typically 1 inch of static pressure. So the 1 inch refers to 1 inch water column, static pressure, that's what we're looking at. So we got, that's your variables coming in right at this inlet box. Okay. And then from that, it's going to go through the damper and all. So you got kind of a big picture. All right. Page. Pressure. 2 different styles of box or types. VAV terminal units. Pressure dependent, pressure independent. What they both do, they can be single duct, like that one right there, a single inlet. Do that. could have dual duct. You can have two inlets. Not used very often, but you could. In other words, you got a hot deck, cold deck, and one of those decks might have 90-degree air, and the other one has 55-degree air. The box in is basically blending. That's all it's doing. And feeding that as a result. They both can do base board heat, reheats. They both have that capability. So that's what they have in common. But pressure dependent versus independent, there are two different styles. What did you learn this week about dependent versus independent? You guys discussed. Is one better than the other? Does it matter? All right, let's talk about that. Let's talk about dependent box first. On the x-axis right here is room temperature. That's seen by the old thermostat, right? Nothing about that. So that's an input into the controller. 75 degrees in this case is the set point I want in the room. Okay, so we got our basic stuff. On this side, we have the damper. What position is it in percent? So we could say that we have some minimum position and some maximum position. As the room temperature goes up, what are we going to do? We're going to open up the damper. Okay, what's wrong with that? All right, let's talk about that. With a dependent box, so the controller has no idea how much CFM is going through. Not a clue. It just knows damper position. It says it's a direct acting response. When temperature goes up, temperature goes up. Now, there's a couple of things to think about on that. The time constant on this, how fast it responds at a room temperature is very slow. In other words, that big classroom you're in, or imagine a big auditorium you're in, how long do you think it takes to change 1 degree Fahrenheit? 1 second? 5 seconds? 1 minute? And more like 5 minutes. Could be longer. Is that something that's a problem with the stat? No. It's just the nature of room temperature. How long it takes for this stat to register and change and upload it to the controller. It could take 5 minutes easily or more. So you've already got a lag built into the response between the time that the temperature went up and the time the damper actually moved. See what I'm getting at? So there's a slower response. Here's the other thing. When I sold you this VAV box, I said, here's the deal. If you give me 1 inch of static pressure, this damper is wide open. I guarantee 1,000 CFM will come out of it. That's fair enough. If you don't give me 1 inch of static, I'm taking all my decks off the table. I don't know what's going to come out of these boxes. I can't tell you. See the problem that you have. So you have to think about, so what if the air handler suddenly has a problem? It's no longer delivering 1 inch of static, but 3/4 of an inch of static. What's going to happen to the amount of CFM coming out? You're going to get less. But the box controller doesn't know that happening. It doesn't know. It's dependent on getting that 1 inch of static, and that's what the term dependent comes from. So this guy, dependent box, is relying on that guy, the air handler, to give you 1 inch of static. So it can't correct this fast. So you got a real bad response on the dependent box. Yeah, where the term dependent comes from.
So it's not the preferred box.
Sorry?
So it's not a preferred box.
No, you're right, exactly right. You got it. So the core absolutely goes independent. Let's talk about that. Absolutely right. Where I use a dependent box to save money, a loading dock. You're living in Wisconsin, it's January. You think you're going to maintain the set point? That's why everyone's wearing jackets all day long. I might do that. I might say, yeah, I'll just get a cheap little box. For that matter, a little old fan combination and be done with it. I don't really care. That's a non-critical zone, right? Now, the office building, that's a different story. So there's where you might use a independent. But you're absolutely right. You know, we're going to go independent. Now, the first thing about an independent box is when you look at it, like right there, you see two little hoses. What that means is you got a flow pickup inside the box itself, right here. A flow pickup is nothing more than a repackaged pico tube. All it is a repackaged pico tube that the manufacturer creates. So you've got your total pressure coming in here. That will be measured on this hose. Static pressure will be on this one. And you can trace down over here. Those two hoses enter into the control room right over here. So what's going on in this one is these are like little holes. Total pressure, static pressure, high side, low side. Remember I said these are nothing more than repackaged pico tube. So I got my total pressure, static pressure. Total pressure is equal to static pressure plus velocity pressure, right? That's just basic physics. So we've got total pressure minus static pressure, because this is a differential, right? Subtract the two. So total pressure minus static pressure is equal to velocity pressure. So what we really have right here is velocity pressure. The difference between these two pressures now is velocity pressure. Okay, and where are we going with this? I haven't finished yet. That's what we've got next. Okay, so far so good on that. So you got velocity pressure. Inside that little controller that you see right there, he's running a calculation. You don't have to worry about it right now. We'll talk about it later. When he's done taking velocity pressure, he's calculating CFM. Now, the independent box, we know how much CFM is going through the box. Okay? Because this little controller is calculating. So now I know how much it is. The next step is, well, what's my set point? How do I know what my set point is? In other words, what's my target? What's my target in CFM? So there's going to be another calculation being done. Well, it looks almost the same. On the y-axis, so what we have is a calculated CFM set point. So let me put some numbers on this. Let's say the requirements for that room is minimum CFM is 300, maximum is 1,000. So the room temperature is still static. It hasn't changed. My set point is stayed the same. But our travel is going to go from 300, delta Y is from 300 to 1,000. So as the room temperature goes up, I'm asking for a higher CFM set point. So, makes sense on so far? So we're readjusting that set point all day long based upon the load, which is what? So let's just say for a minute that the calculated CFM, actual CFM, is 500. as seen by all this circuit. Inside the box, let's say that he says, well, my calculated CFM based upon their room temperatures, I need 550. What's the box going to do? The damper open or close it? Don't open it. He says, I want 550. He says, oh, I'm actually getting 500. He's going to open up the box. See how that works? Now, here's where it all comes together, I hope. Let's say suddenly the inlet to this box, the static pressure changes. It's no longer 1 inch. It's 3/4 of an inch. We know right away that this is going to do what? It's going to go down. Now he's saying, well, I've got 450. He says, yeah, but I want 550. So what's he going to do with the damper now? Open it some more. The whole point being, pressure doesn't change in minutes, it changes in seconds. This is a very fast response. So this thing can adjust for any kind of changes that it sees in the inlet of the box. Therefore, it's independent of the pressure fluctuations of the air handler. And that's the whole myth legend behind the first handler. Mr. Allen's right. That's the one you want to use because it can adjust to give you better accuracy and more efficiency. That's how we all come together. Kind of makes sense as far as independent versus multi.
How significant is that cost difference?
I'm sorry?
How significant is the cost difference between the two boxes?
The cost of the box is, there's going to definitely be a cost because you're paying for the bolt, they're paying for this voltage. I can't give you actual dollars, but when you think about the 20-year span that box is going to be there, it's a payback.
Yeah, I was just curious, if it was really saving that much if you were doing pressure.
I don't think, when you look at the fact that, this machine here, they got to build this, I can't see it being that significant when the payback is 20 years of getting accurate flow,
Right.
and you're managing your energy much more efficient. So I'd say it's a definite payback, which is why the Corps recommends independent, which is the most common. Good advice. Okay, so that's what the two are called, what they're about. Just so we know, what's this little thing about? Well, there's a little calculation going on. That calculation is right there. So let's talk about that for a minute. Cubic feet per minute is equal to what? Feet per minute? Times area, and that area is going to be in square feet. All right. Feet times square feet is cubic feet. That's nice and easy. Feet per minute is pure velocity. You're driving down the street, you put your hand out the window, that's velocity. That's not cubic feet, that's just feet per minute. Right? But I want cubic feet. Well, I'm going to drive down the road and put a piece of ductwork over my hand. Now I got cubic feet. You get the idea. Because I've exposed that. Now I got a volume to there, not just velocity. I've got a volume. So we got to break this down. Feet per minute is an airflow constant of 4,005. It does change about every 5,000 feet. It's about 10% less, roughly. So if I'm in Flagstaff, Arizona, which is 7,200 feet, they would not use this number. They'd adjust this number. But we'll assume for me it's more at sea level or close to it. This quantity here is feet per minute. 4,005 times the square root of the velocity pressure. Velocity pressure by itself is a nonlinear function curve. They think the square root of it is linearized, and that's why they think the square root. Okay. So this little guy here, the controller is calculating the velocity at feet per minute first. This times area. In feet squared. Okay. And that's what we're going to be dealing with. So now, since we all know that 99% of the inlets to boxes is what? Valve. So they just got to convert around to square feet. So you can either use a chart like this and saying, well, the inlet to the box, we're talking about this right here, the inlet. If that diameter is 10 inches, that's 0.545 square feet. You'd have to know that because in the software of that controller, I've got to input that 0.545. If you like to fool around with math, pi r squared divided by 144. For HVAC, that's fine for pi. So I can say, well, what's the radius? Well, if it's 10 inches diameter, this is 5, so 5 squared times pi divided by 144. There are 144 square inches in 1 square foot. Remember, you're looking for a square feet. And that's it. And then you input that number. Now we deal with the required on that. Now, I got to go back to this. It didn't quite give you the whole picture. If you look over here, something called a multiplier. It's also called a K factor. It's also called a pickup gain. It's the way the industry works. But anyway, we'll refer to it as a multiplier or a pickup gain. It is a number, it's a pure number, that the manufacturer of this box assigned to this focus box. Now, why do they do this? Well, you've got to remember that the velocity pressure, when that damper is really pinched down, could be in the hundreds of inches water column. Whoa, that's almost like blowing up a balloon. There's hardly anything there. So to get a more accurate reading, they actually boost the number. They actually multiply it. They do it by the way they make these holes. Not done through electronics. It comes through this way. It's very clever how they machine these holes. That will actually multiply this number right here. It might be like 2.1. So the velocity pressure multiplied times 2.1. Or it could be 4.8. It's all different. It's a number that has to be known. Now, of course, if you go online, just go on your phone, you can go online to get that information. For the purposes of what we're doing here, we're going to actually calculate. Okay. So far, so good on that. So, in other words, whatever you multiply here, what are we doing here? We're dividing it out. So ultimately, you've got to mathematically get rid of this number. Because you don't have the actual velocity pressure until you divide this into it. Now you've got rid of this effect right here. So they divide this into the velocity pressure, that's square rooted, times 4,005 times speed. We're going to be getting into that much more in this second. Now, let's backtrack just a little bit. If you're falling asleep, I understand that, but here's a takeaway. This is something don't fall asleep on. The takeaway is this. That number, that number, that number. You absolutely have to go. Bear with me. This is almost done. Okay, this number, that number, that number. You have to go to each room and verify. Okay. So what that means is, let's say you're in a room, you're going to have the tabs person there with the flow hood, right? And you're going to tell the tabs person, drive the VAV box full open. And he's going to do that, and you go to each diffuser and add up all the numbers you see out there. That better equal that. Okay? Now go have the damper go to minimum position. measure all the diffusers, add them up, and they should equal that. If they don't, you don't sign off on that job.
So
You
you're
don't sign off on
checking it
that.
against the controller.
Sorry?
So you're checking it against the controller.
Yes, well, you're checking with the flow rate.
Right,
Really?
but you're checking the flow rate against what's input on
Yeah,
the
that's
controller.
what you're doing, you're matching it up. And you're saying, well, I'm supposed to see 1,000 CFM, I don't see it, we're done here. You don't fix the problem, they're gonna fix the problem. But you're not gonna sign off on that room, because you cannot satisfy that zone. If he reads like 800 CFM, you're starting that room by 200 CFM. In the fall and the spring, that might work. It won't work in the summer, it's 110 outside. So that's why you gotta verify on that it does in fact do that. Now think about this. When engineers are designing a system, mechanical system, are they designing for fall and spring? No, they're designing for design days. When does that happen? In Wisconsin in January, in Phoenix in July 4th, that's when they're designing the system. That's how they figure it out. So how do they come up with this number right here? They do load calculations. 500 BTUs per hour, 500 BTUs per hour, 700 BTUs per hour, 3.4 watts of BTUs per watt. They do a load count. And they figure out how many BTUs they got to move or remove, whatever they got to do. From that, they determine the CFM. So you can see that if you don't get the right number, you're going to starve that room. Which again, in fall and spring won't be such a big deal. But in the summertime, it's when you're going to pay. You're going to get hot calls. That's why you guys got to be there to verify that you in fact are getting these numbers. Plus the fact is, what is the temperature? So you ask yourself, well, where do I get these numbers? In your student notes, you have a tab called Gateway Lab Room Discussion. Once you find that tab, it should be 11 by 17. Go ahead and find that. There should be a tab called Gateway. Gateway with Lab on the schedule. Oh yeah, that's oh, there you go. Good. Everyone got it okay? All right. So let's say you're in room 106 right now. You and your commissioning agent and the tabs guy. Look at room 106. We come down this way and come down this way. We're getting information. What's important in 106 says my cooling minimum flow is 550. So now that means we would change this number to 550. And the maximum flow through this box in the summertime will be 1100. So now we're traveling from 550 up to 1100. That's how you know which numbers to use. And oh, by the way, we should be getting 74 degrees in the summertime in that space. So what you do, simply like, I'll go through the scenario again. You're in summertime mode. You ask the tabs guy to open up the box fully, add up all the CFM from the diffusers, and it should equal 1100. Okay, go down to the minimum, do the same thing, add up all the diffusers in that zone, it should be 550. If you do not get these, then you walk, you don't sign off. And oh, by the way, we better have 74 degrees in that zone. Okay. Now, you can also check out the winter mode, or it's the heating mode. Notice it's got a different minimum CFM and a different maximum. The reason for that is simple. Remember I said during the year, all year round, there's 55 degree air coming in the air. We know that already. What we're going to say is, well, when we have a call for heat, I'm gonna pitch this damper down to 100 CF and 550. I want less of that 500. I want less of that 55 per year. That's again what I'm doing. Makes sense. I'm pitch it down even more. Only during the heating cycle. And I'm not gonna open it up more than 200 CF. During the winter now. So I'm gonna keep as less of this air as I can. You're not influencing the dampers that the main air can work. You're not touching those dampers. It could dampen the air. So those are crucial too. But now you know what numbers you should have. Any questions so far? Documentation. How many guys have been out checking rooms? Oh, okay. I assume you've got this document, right? Yeah. Don't bother showing up without it. What's the point? There's no point in going. If you ask me to go out to Tempe to check out some rooms, if you don't give me this, I'm staying home. What's the point? I have no idea what I should have. That's all. Again, that's all part of what you're submitting. You're gonna have a copy. CAP style a copy. Control style have a copy. So everyone has copies. And then you make your changes according to any of your lots of markups on the schedule last week. That's pretty much the most important thing. We're going to come back to this in a moment. Before we do, let's want to do it very hard. All right, let's go back to your student notebook and where we left off. We have this page 4, go to page 5. Oh, yeah, go to page 5, sorry. Okay. You can have a style of box that has fan assist. There's 2 types of fans that you can have. Okay. The first one is series fan. Excellent description. You've got inlet air coming in here. And right after it, there's a little booster fan. Fractional horsepower, 120. You might have 3 separate speeds, which is set by the balancer. All you're doing is pushing more air out. Okay. That fan, though, is controlled by the little controller right here. Now, when does it turn on? It turns on when this box is told to go occupied. People are going into this space. No, this does not have a software clock inside. It does not have a time clock inside. It's told to go occupied from the head end, which we'll talk about tomorrow. How does he get that information? Well, through a communication bus right there. That wire ends up going to the head end. And it does have a weekly schedule. So it says, oh, it's Monday, it's 7 o'clock in the morning, it sends a signal to that bus to tell that controller to go occupy. When the controller gets that information, it takes a series fan and turns it on. And it starts to operate the dampers. How does it know when to go unoccupied? The same way. There's going to be a weekly schedule in the head end or EIS system. The signal is going to come down here, tell them to go unoccupied. They'll turn the fan on. And that's how it goes all day long. Now, let's talk about this guy. Okay. You notice in that room schedule there's 2 set points for the temperature. 74 degrees would be for cooling and 70 degrees for heating side. Okay. When we go below 74 degrees, the damper does what? It's going to stay at that position. Okay? That makes sense because you don't want any more of that 55 degree air. Right here, the fan goes on. So immediately on a call for heating, you see the parallel fan right here will start to turn on. What's he trying to do? Well, he's trying to cool inflammatory. So you have the inlet air here, the parallel fan, which is parallel to the flow right here. It's going to turn on to pull in inflammatory. The air right above the ceiling tile, right? He's trying to get the free heat again to do what? Well, I have a call for heating, so I'm going to turn on that fan. And then hopefully that'll be enough heat to use to so it's parallel. The first one was series, right? Back of it. The other one's parallel. It's turned parallel. The whole thing is when this temperature goes back up, it goes off. So all day long in the winter, it's cycling. It's cycling based upon the call for heating or not, which is determined by what the little staff is. See how that works? Okay. So here's another application. I'm going to add to this little scenario. Okay, imagine what you're looking at the roof, the core of the building. Right? We know as you go into the building, there's going to be interior zones and there's going to be exterior zones. Let's imagine we're in Fargo, North Dakota. Okay, cold area, wintertime. Right now it's minus 20. Okay, not reasonable. So we know we've got a big heating load on the shell of this building. Right here, I've got thin tube radiation units, right? So what we're going to say is the controller, the box controller has to tell these valves to begin to open up. So what can happen is something like this. Maybe down here at 68 degrees, it starts to call for baseboard or perimeter heating. That could be hot water or it could be electric. So what are you doing here? Well, you're opening up these valves, and we're only talking a half-inch, 1-inch lines, 3 or 4 GPM, and you got a thin tube radiation unit in this case. So the controller says, first thing I'm going to do is turn on the parallel fan, try to get free heat. I'm not getting enough, it's still dropping. Now I'm going to do what? Open up my baseboard. So now the thing is going to start to do what? Proportionally, open up these valves to get more heat. Well, what are you doing really? Well, you're radiating heat first of all. So you're not making the whole room comfortable, but a little bit. You're putting up a wall heat, aren't you? Sure. What are you trying to do? Help out the differential pressure between here and here. I'm sorry, differential temperature. Because maybe you're trying to maintain 70 degrees in here to minus 20. That's a big delta T, right? So we're going to try to get this heat back up. So this blanket or wall of heat going up the side in the room is going to be helping out losing the heat, as well as doing something else. Yes, it's going to put up a blanket heat to help heat loss in the space, right? What else is it doing? It's minus 20. Surface, let's say this is all glass. What does that do to the surface of this glass? It's real cold. What does that do to the dew point? It drops it big time. If you have moisture in here, it's going to do what? It's going to condense. If it condenses and you don't have this, you're going to have ice on it. I lived in Wisconsin, trust me. Trust me, man, I know. You won't be able to look out those windows. So that's another reason for having baseboard along here. Follow me on that? Now, if you might have reheats, like as shown right here. So we've got a VAV box. And I actually have a little heat exchanger, a little heating coil. And I got a little valve right here pushing out hot water. The same hot water that's here is pushing in over here. So I could say that, well, what if the baseboards aren't cutting it yet? Well, of reheat. So now I got my reheat, I got these valves opening up here. Over here, I've got my reheats going on. And that should bring your temperature back up to where it should go. So the sequence goes parallel fan, baseboard, and reheat. You can change this. You can say reheat followed by baseboard. That's up to you. The controller doesn't care. Or you might just find, well, we only got baseboard. That doesn't matter. So my point is you can change this any way you want to. But if you have full out baseboard and reheats, that's how they would set the sequence. That's what we wanted right over here. We got right here, it's the thin tube radiation unit, and then we got our reheat switch. You guys doing a lot of work with baseboards, reheats, especially guys up north? You see how they're set up. Here we're showing this scenario where we only have reheats. So in that case, if we don't have baseboard, you'd have reheats over here. So then you'd have your series fan, in this case not a parallel fan, but a series fan, followed by a reheat on the discharge, and you're good to go. Again, I emphasize that you might have hot water. It could be electric. Okay, down here, we do a lot of electric on that one. But we have a different kind of configuration. It doesn't matter to the software. It doesn't matter. You just got to tell me what you have, and I'll program it up. If you need to verify this stuff is working, you can do that. And how do they do that? Well, one of them in my summer mode, how do I get my heating stuff to work? Real simple. That room temperature, with my laptop, I can override it. I can fake the system out. I'm saying, okay, yeah, in reality it's 76 degrees in this room. I'm going to override that to 68 degrees. And then you verify that this stuff works right. So you can't do it. You can check out heating, another type of season. So I can check out heating stuff during the summer and vice versa. That's not a problem. And that's what you want to ask them to do. Ask the contractor. So you go, okay, make this room temperature operate in the heating mode. With a laptop, and did this happen? It's actually happening. You may not have hot water going through it, but you can look at the valves. So you got to get down to that level. You got to feel that honey back all the way down to the level, so you know everything's working. So when it comes winter time, everything will be okay. Questions on that so far? Yeah, this is just electric heat. We just talked about reheats, so you've got electric heat. Basically, you're going to be staging, meaning you're going to have binary output, stage 1, stage 2, stage 3. You might have like 1 kV for each stage, and all that kind of stuff. So they calculate how many stages they need, and they figure out how much heat they got to make up, and that's the way it would go. The only thing you have to be kind of careful of is right here. The VAV box manufacturer, like electric heat, will have safety in it, separate from my controls. And they're set up to saying, I got to have an minimum CFM for each KW, or I won't turn the stage on. Because last thing you don't want to do is have a stage come on and not have airflow across it, or they coil up and have fire. So you don't want that. In this case, you're saying, well, you got to have at least 70 CFM per KW. So for some odd reason, you weren't getting enough flow through the box across those heaters, they can turn on. But there's something you have to do. Otherwise, it works fine. If you're ever going to do it, but if you ever have to go work on this thing, you got to be completely covered in PPE, all your protection gear, and stuff. The Johnson techs hate it, but they got to do it because imagine if you're 10 feet off the ground, you got to wear a smock, you got to have a shield, and leather gloves on that itty bitty keyboard. They used to hate it, but there's nothing they can do. But anyway, yes, high voltage, if you're talking 277 on up, so this thing, oh yeah, every time. Let's see, I think that's. Here's a little functional performance checklist, if you want to call it that. Here's the kind of thing you need to have when you offer a job. You're saying, hey, it's my first VAV box job. Well, get something like this. I know the Corps has them. What is the checklist. What's a cheat sheet? And then remember I said the goal of our class right now is what questions do I ask the contractor? That's what you want to know. Starting out right here, it's a connected diffuser over there. Match the VAV box required. Is its size right for that? Okay. Have the CAD guy show you the specifications. Does the required CFM is seen as what? On that room schedule, right? Does that match the actual CFM coming from the diffuser? Right? We talked about that. How about the minimum CFM? Is that been set for heating? Continue to get verified according to the room schedule. And so on. If the box is pressure independent, does it have at least one inlet static? Yes or no? And you just go down through this whole thing. Have they been recorded? This is all updated. Maybe there were changes made. I want an S-bill. I don't want pie in the sky. What does it really say? So make sure those things have been noted. Now think about this. You're there on the opening day, right? You're there for the installation and final verification. What about the guys who come in after warranty? The guys have to do service work. Well, they want to have the right values on that room station. That's why when this gets passed on to the next group, they have actual values to put in, not pie in the sky values. Get the idea. Kind of put yourself in their position. Service guys have one of the toughest jobs. They inherit all these problems, so you want to make sure he's updated. These guys get a fair shake of everything. And so on, you come all the way down. This is a nice little question sheet that you can use when you get out into the field. So, any questions so far?
What about labeling?
Sorry?
What about labeling?
Yeah, I didn't have that there. This could be more labeling. Yes, absolutely. Again, think about the guys who are going to inherit this job. Yes, sir. Absolutely. Labeling everything. I mean, right, not only right here, of course, but everywhere. Labeling on the power strip, right? The incoming power. We're going to talk about disconnects tomorrow. Absolutely. All that stuff has to be there. Again, think about the poor guy who's coming in and inheriting this job. That'd be easier on them. Absolutely. All right, so what we're going to do, one other thing. One other thing. Let's say you're going, you know what? I like to get home and go fishing. Tell you what, we'll check this room out if they got in. It's not bother going out there. Hey, that's a great idea. We'll just drink coffee, look at the head end, and we'll just check off the rooms as we go. Keeping in mind your room has never been signed off. Okay. So what's this screen? I'm going to illustrate something. Well, this screen is this is a window of my laptop looking into that controller. I'm looking at all the numbers in real time. All the things that are going on. I can see what's going on in that box right now. This guy here called process variable. That's nothing more than CFM, as it says. That's the calculated CFM we talked about earlier in the afternoon, right? That's what the box controller thinks it is. 371. That's the number that will be mapped back to the head end. So you're in some computer room and you're looking at it. That's what he's going to see. If you don't go to the room, you're going to say, hey, look, looking for 180, you got 171, that's 5%. Let's sign off on the drum. Really? Okay. Need a volunteer. Anybody would like to? Sure. With this little gem, you just do the IO button. If you need to get a reading, you can use the red button. So let's take a look at this room. So go ahead, snug that up. Okay, so this gentleman said, the phone says it's 75. No, that can't be right. It's got to be 171, right? No, we all know if it's been calibrated, you go to the floor bed. So we know in reality we got a problem. But if you signed off from the head end, you think that room is good. And in reality, we're starting this room. You get why you want to do this in the room. Once you sign off on the room, yeah, use the head end, of course, at that point in time. But your data won't be reliable. So if something's wrong with that controller, you haven't figured it out yet, but you guys are actually going to solve the problem in the lab. You're going to be doing that. So I'm trying to illustrate why you never commission remotely to go into the room. Okay on that one? So far, so good. So this little screen here you're going to be working with, and it's going to be you're using my laptop, so we're all set up to go there. So before we do that, let's go back now to your labs. On page 10, you'll have this. So what we're going to do is, we got one group here, we got another group over here. One group is going to be walking up and down this corridor, starting with that diffuser down there, and each diffuser's been labeled from 102, 101, all the way down the line. First thing you're going to do is take the flow hood, and you're going to start back there and record your CFM. You'll also get temperature values from the flow hood. You'll get both. Fill it in and add them all up. That'd be one step. The same group who's walking up and down will be filling in this table. So, room 101, which is down the end here, if you've got a single inlet, you have repeats. On this side of it is it pneumatically controlled, DDC controlled, or pressure independently repeated. And you're going to fill out all of this whole table. That you're going to do by observation, going up and down this corridor. Then you're going to use the room schedule to fill in this information. Now you don't have to go to these boxes, but the information you need for this table is on the room schedule. Okay, so you got to transpose that over to this area. Okay, that'll be the group that's walking up and down. Okay. Now the other group will be here at my laptop. First thing is, they do not have to do number 2. If you have time, I'll get back to it. Let's skip this part, so we want to exit this out. So the group that's sitting over here or standing over here won't have to do this lab. But you've got to do this lab. So you can fix out this one, go to step number 3. And you're going to start on step number 3 right here. This is where your lab will start. Now, so what are we doing over here? All right, the goal is this. We already saw that this number's bogus. This number's not right. So what we're going to be doing is changing this number and this number. They're in the area, square feet, and this is that multiplier, also called the pickup rate. We're going to change these two in the slab such that when you're done, you take the flow hood, measure right here, and compare it back to that, and you should be within 5%. That's your flow. Right? How do we do it? Let's go through this. Go through the lab. We're going to be dealing with this box, that diffuser. The inlet right there to that box is a 6-inch inlet. Go back in your student notes and figure out what is that in square feet. We talked about that earlier. Write that down. When you write it down, when you do that, you come over here. You double click on the area, whatever you wrote down, enter it right here, press override. Like override. Now you're going to wait a couple of minutes. So you enter this value in the software, wrote it down, wait about a minute, and then use the flow hood. Again, take the flow hood, measure the CFM coming out of it. Right? And you're going to write that down. Final step is look at the differential pressure, which is right there. So now you've got the CFM, you've got the area change, what is the differential pressure, and you write that down. Okay? You're almost home free. You just gotta plug all these numbers in. Flow coefficient is 4,005 times the area divided by the flow hood that you measured. Divide that out. Don't forget to square it. Not to forget to square it. Multiply that times the differential pressure that you have right here, and you'll have a new pickup meter or multiplier. And guess what? All you're going to do then is come back in. Come over here. Enter it, override. Wait about a minute. Okay. And what you're going to do then is wait, take the flow hood, compare that to now the new calculated value. It should be around 5%. So I don't care. This group can be working here. This group can be working up in the corridor. When you're done, just swap. But everyone's going to get a chance to do this. Okay, yes, sir. Yeah, you'll actually get from the flow hood. Yeah, that's not the supply area. It's not supply area. It's the actual room temperature, which really is. But yeah, that's what you use. Just use that from the flow hood. You're good to go. So I'll let you guys work it out. Again, the corridor 101 starts going over here. The other guys can work right over here. Fluids right over here, and then you're good to go. Okay.
Number 3.
Great.
Example system. This is a box of dribble flow. Rotate like this, all the air coming off the top. Over and on boom. They first put it in, it runs down up to max. Because we got enough airflow to run the last one. At maximum airflow. So what they did was they got
Double click on this again. Just double click on there you go.
So they put in, they took the elbow off, and then when they put those cascading lighting things, they were talking about it. Like that. Goes like this, goes like that, goes like this, like 1, 2, 3, 4, 7 little pieces of stuff. And it's taken enough of the simple cut away where now they can actually use it
Wait.
Now,
Did you know you said you calculate? How did you
saw
solve
this.
this? We got to start with the area.
What would be the best thing with your area? Recommend that's quite often.
Oh, no, yeah, you're starting on step number.
Oh,
you're right.
I yeah, well, sometimes you won't be on it. Now, see if it comes with a problem about this right. Because we just like that. In here, in there, we just like that. 2.5 duct fans. And it's all big. So this we should be, should have a top. Now, what happens, so much of this equipment has been donated to college. They buy very little of this stuff. What they do, they get it up. They cut all this. So when they come up, they say, hey, do you want this? They usually take it. They had one time, they had a box manufacturer, I don't know if it's Tyson or not, in Texas, called them up, wanted to know, they had a whole bunch of college box. Wanted to know if the college wanted it. All they had to do was pay some shipping. So a lot of the stuff is hanging up here, these boxes that they got. So this way,
Are you getting a reading?
so if you take a look, you see all the stuff. Okay, let's hit on that. Well, I had one of this like 10 years. Box of this stuff, this was about 2 months ago.
Why don't you guys come over here? Help them out. Let's do all the work here. Okay, work together on it. See,
Say what?
Part of this equation is 5 plus 3.
I think we'll have enough to do it, huh? Do you want to give it to him?
That's the first thing I'm doing. So,
He gave us the two able to flip the layer. That's super good. Right.
saying 77 doesn't sound right, does it?
Yeah. Well, then one of what you measured that, I think he had 78 or something, he did. Well, it might be different, but it's each
Yeah, we usually keep the code just like this.
Oh, yeah, divide by 3 on the one. Different spots in there.
Which is a water valve, yes. Problem is, this is something.
Right, so this is the water column.
That's like which is per water. So we need to do a special. It's pretty.
There's another flow that's sitting over there.
all right, guys, check your book 102 and see what you guys are getting right here. Just push the red button. Don't do the read button. Do the red button over here. Yeah. Another second. Okay, so you got 134. No, you haven't got it. So recalculate. Use 134 for your flow hood CFM.
Is this?
So you want to put
It's supposed to be PSI.
no, that's what you want. Now hold on a second. So your new CFM right in here. What 134 we said? Yeah, put 134 in there. Now also not done yet. Oh, the VAV. This is the new differential pressure. I'm going to put that in. Differential pressure is just water now. And I'll put that in over there.
And then you want to divide that by 12 to the box area and then
Well, yeah. Now, what's your hold on. So what did you get? That's right. So you take 4,005, okay, times your area, right? 2196 divided by 134. Square that value. Square it. And then multiply that times your differential pressure. That number's way too big. Let me see what you do. 4,005 times 0.196 divided by. Okay, what did you get for that?
5.85.
Square that.
I'm sorry. Yeah, I did it.
And multiply it times the differential pressure.
Okay. 2.73.
What you get?
2.73.
Try that one.
So that times this has to be units.
Now, wait a second. Wait about a minute.
We need that book again.
So there's one of them. A little longer. All right, take your reading now. Use the red button to get a new reading. Let's see what we got. About 170. Okay. You're pretty close to 5% of its total range, so you're good to go. Okay. Why don't you guys then swap labs and do what these guys are doing? I'm going to change the numbers here so you don't, they don't get your work. Go off the chart. All right. So yeah, you guys start to the other labs. I'll change this.
The other side.
Well, the lots of system like that. So that's interesting too. I think you're just sitting ready, man.
Yes, sir. I'll do a review in 2 minutes. Alright, clear.
When you jump to 412, 413, what do you call it, 407?
Inspections on the other part too.
Okay, guys, about 5 minutes, we'll go over this. Oh, you haven't done this yet? Oh, go ahead, guys, yeah. 10 minutes, we'll go over it. Yep, go ahead, guys. All right, guys, go ahead and take a flow hood reading on this 10102. You got your area, right? You got that in. Yeah, you don't have to click anything there. We now calculate your pickup gain multiplier. You know, your differential pressure is right there against your corner block. What'd you get for your pickup gain? 3.2. Okay, go to the next. Now wait about a minute. Give the system a chance to settle out.
That's about right.
Yeah, go ahead, take your reading now. Got 184. What's that? 184. He keeps you 178. You're within 5%. Perfect. Perfect. Good job. Couple minutes, we'll go over this the other lap, so you're good to go. Good job. You nailed it. Oh yeah, we did. Yeah, you did. You got the right paper. Yeah, that's why I didn't have you do that second step. We didn't change that in the software. The main max dot nine. Everybody here. All right, I just kind of go over this and then get you guys out. Looking back at this table, let's start right here. Tell me about room 101. What do we got going on in room 101?
Single ducts,
Okay,
no fan, no reheat,
okay.
pneumatically controlled,
Controlled and dependent or independent?
independent,
Independent. Room 102, what do we know about it?
single duct,
Okay. BDC. BDC. What else do you know about it?
independent,
Independent. Room 103. What do we got going on in 103? Single lift, right? No reheats, no that good stuff. And over here, BDC. Room 104 is a little different. What do we got going on in room 104?
series, a reheat there,
No, not a reheat. But somebody said series stand. So we've got a single duct. We've got a series stand. No reheats in that. And over here, what do we have? Do you see? Independent, right? What's using that room 104, when you look on the side, it looks like there's a box there that would contain the circuitry for reheats. That's really the speed controller for the fan. That's all it is. Number 5, tell me about it.
single duct,
Okay?
BBC, independent. There's series fan in that one too. No.
That's pretty much it. Were you able to get the details on, this is the transposition of that little schedule, break, everyone able to get that okay?
He was asking for the series.
Oh, sorry.
A series thing on 105.
No, not 105. 105 is a cooling only box. If you were to go down to room 106, which is where Jim is teaching, that's not ducted, but that has a parallel fan, and it's got electric reheats, but since it's not ducted, it didn't have any going down there.
So in summary, all the ones we did, there's no reheat on any of them,
No,
and there's only one with the series fan.
that's correct. Got it. All right, any other questions? All right, guys, thanks for being here. If you gotta come here, this is the variable air volume air handler tomorrow. If you do decide to come here, bring your student notes and enjoy the night.
Thank you.
Yeah, get out and do something. All right, thanks, Dave. All right, guys.
So what part of Wisconsin?
I'm sorry?
What part of Wisconsin? were you?
Oh, I lived outside of Milwaukee, so that's where I started working at the 507 building downtown, which is right along the street. That's where the home headquarters.
45 minutes west of Cross.
Oh, the cross. I know where that is. Oh, yeah. My pleasure. Yeah, no,
First 20 years of my life, and then I came back to do on.
okay. It's beautiful up there in the fall.
Yeah, I think time is I'm not
All the way.
But the thing is summer thing you have compared to what Arizona and North Carolina or
You know, if I look at it like this, when I had a chance to retire here, I was still working for Johnson. Come down and work my business right here in that building. I just look at the point where 3 months, three seasons are gorgeous. We have one of the seasons. You don't have to
9 months of the year is miserable.
Yeah, here.
No, in Wisconsin.
Oh, yeah, here.
That is horrible.
And I told my wife, I don't have to shovel 100
I don't even have to mow lawn here.
No.
That's one thing too, is I said, I bet you I can't even find the loads of a lawnmower.
When I was moving here, my son-in-law, they lived in my daughter lived upstate with him. And I got great dessert. I said, the last day living here is leave. I said, Pete, bring the trailer. He brings his trailer, and on the driveway was my snow blower and my lawnmower. I said, remember I said someday this will all be yours? And then he snarked it.
It's happened.
Well, Lowe's, man,
Oh, that's
that's
cheap.
$800, man. That's a lot of money.
Yeah, it's not cheap.
But he took them, put my lawnmower, and said, I won't need either one of these.
I'll gladly give it to you.
Yeah, I'll see you.
Thanks for
Yeah,
the
have a
time.
good evening.
How did the soft shoe dance go today?
You're doing good. They're good guys. Yeah, no, I think they're really good. I might be problems with their
What do you got to do to the customer?
Oh, for tomorrow.
Well, that's what-
Yeah, I just like to set them up on the first day and then just go there. So I'm going to use them for, in this class, since there's no walk presentation on head ends, I do about a 20-minute overview of head ends. And then I don't do like that area.
Right.
And then I use these guys to get it to be.
Now, is the lighting too dark in here?
Yeah, well, tomorrow I'm going to have to pop that light on.
Well, at least everybody on it, just that it was bothering. What I gotta do is I gotta split these lights so we can have them on.
Okay. Yeah, because right now it's fine for the screen, but not for getting around
Right.
there in the dark. So I,
Well, I gotta take to be able to have this end of these lights switched up.
okay.
So, but I didn't see it until we started looking at it from a camera point of view of the fan.
Well, I can see why they did it. They didn't want to get a backlight as cameras. I'm like, today you can do it, but now tomorrow you gotta come.
Well, we just gotta figure out a way to split them and put another switch down.
Oh yeah, no, that'll work out. But everything's working just fine. I mean, I don't have any problems at all. And I didn't expect it for this class to have
Yeah.
we've always been going.
Yeah.
So I don't know how many guys I got here tomorrow. There were a couple of guys that said for sure, but I don't know how many I got.
Well, they have a list of who's gonna go where at the beginning. But a guy put them on board.
Yeah, that's okay.
They gotta go where they wanna go.
Oh yeah, that's fine. You should. It makes sense to do that. But I know a couple of guys were asking about this particular lab here. Oh yeah. No, I thought playing. They're good guys. I only had one guy up a little bit of a sleeper, but I kept him away. But Mike, the Ziegler was telling me the same thing. I know what his guy is. The rest of them were good.
They're all, doing what they're supposed to do.
Name of the game, right?
Oh yeah, yeah. And Walt's got a heads up. Casey's got to do the recommendations, which is pretty easy.
Yeah, no, it's pretty easy. And there's not a lot of people who want to play.
Yeah, I don't even know how many he's got. So.
Not too many like this one. That's not good.
Were there guys signed up for this one? The VAV tournament?
Oh, yeah. Well, you can't. I was trying to understand how they were trying to break it down.
Right.
But we'll just have to see how they go. You may have golf guys.
Oh, okay.
I don't know if that's
Well, we'll work out the sharing. Yeah, I mean, different. And never a dull moment. Everything worked okay out there?
the only thing was, well, the boiler is
Oh, yeah, he was saying.
that boiler's supposed to be replaced. Supposed to be replaced before we get in January.
Really?
Oh, yeah.
You want to lock up that little cabinet right there?
Yeah.
Okay.
Yeah, it's supposed to be installed and running before the third January.
Whoa.
Now, we're supposed to have, have you seen the air cold floor out? We saw the air cold floor outside. If you're out there, you would have that platform all the way around
Oh, yeah.
on both sides. On this side and across the end.
We're gonna put this in record. Stick it back in the room back
Yeah, back in the room.
put it.
Oh, yeah.
Well, I just didn't know. I mean, things change in a year.
Oh, no, it's in that room and then you put it in one of them.
Okay. And it's just been, like I said, for the year since I was last here, and I'm sure that things haven't changed.
No, they haven't changed that much.
Okay.
There's a lot of changes made, but not that much.
Not that much, okay.
Nice. Get the boiler in there. Jeez.
No,
That would be super sweet.
I'll see you in about a
Oh,
month.
yeah. Oh, I'm sorry about to see you tomorrow.
No, I'm not gonna be here.
Good. Happy trails getting out of here. And yeah, I'll see you in about a month.
Yeah,
sure.
Okay.
That's fun we're gonna have.
Yeah, it's gonna be interesting. Those the last two days, you know, the first February is it's only like a week between them. Less than 7 days. Really just we'll get done Thursday night and pick it back up Wednesday morning. 6 days.
Oh, well. All right, I'll see you then. Have a good one, Jim. Okay, and yeah, have a good Christmas and everything.
Oh, yeah, I'm hoping they'll see.
All righty.
Did I tell you what the best evaluation I ever got was? It was like this, and at the beginning there were 3 questions. The first question was, what are the instructor's strengths? The second question was, what are the instructor's weaknesses? And the third question was, what can be done to improve both? All these people, one student said, what are the instructor's strengths? Nothing. And then, what are the instructor's weaknesses? Nothing. What can be done to improve the course? Fire again. I got an ad, I got raised. That guy, whoever it was,
Yeah. All right. Not sure I can help that. Yeah. Work today? Yeah. That was so good. What a compressor. Oil everywhere. Yeah, we had to, yes. I keep it. Yeah, but the rest of it, and work. Yes. Yeah. Yeah, he really did figure out why. He was only a 2-year-old person. So we sent him off Oh, pick a price. Go ahead, pick it. They don't need hardly anything. Yeah. No. No one will be able to identify.
And you're number 50.
Yes, it is.
Chelsea, you're hot. Just 10? You know? 28, 30. Okay, I'm hot.
don't know. That's it.
What?
Sorry, you got the bus here.
You get your card ready? So we got turn in here? Did you get your beans ready? What? Can you see that?
Yeah.
Okay, I'm not gonna say it again.
You did turn on? He did turn on. I don't know if he, well, we'll see. Oh, the evaporator won't turn on until it's certain fast. Eddie, are you taking your measurements now or have you started? Okay, get your water color straightened out. There's no reason for, yeah. So far, it's through. So, all you got left is making measurements. So just take the measurements together. Yeah. Well, he can help you make it work. Would you two? Everything was. I was told that. Yeah. All right. So why don't you just help me like Thank you. I appreciate it. So then that way you'll at least the two of them together do the reading stuff, and that's all we got left to do. So to make it work. All right, so go ahead and now you guys have your other report. Yes. Thank you so much. Turn that on. Alright, cool. Yeah. I'll put this back here just in case. Wait here. Yeah. Alright. So what are you doing? Get him out of here. Hey, we've got some refuse on the board here.